Santhan Krishna sir.
Good morning, sir.
Sir, good morning, sir. Sir, we will start at 9:30, sir, exactly.
No problem. I am ready and I checked my camera. The thing, only thing is, you have to give me the presenter rights.
Yes, sir. Yes, sir.
And then you have to check whether my PowerPoint is visible there.
Okay, sir. Santosh, sir.
Not.
Santosh Kumar, sir. Sir. Santosh, sir.
Charbatra sir, Japan sir. Hello.
Yes, sir.
Sir, please give the chance to Sir. Sir will check this PPT.
Sharing. Yes, sir. Now.
You have given me the sharing.
Yes, sir.
Now, whether my PowerPoint is visible?
Not
No,
yet,
sir.
sir.
I put my PowerPoint. Is it visible?
No, sir. Not visible, sir. Yes, sir. It is visible.
It's visible now. Okay. And my speech also, this one voice also is okay.
Okay, sir.
Thank you. Thank you. I can switch off my video, you know.
You can.
Start on-site recording and stop on-site recording, sir. You manage yours.
Hello.
Good morning, all. Good morning, sir.
Morning.
So, welcome to the day 4 of the FDP. I'm privileged to introduce the session speaker, Sri J. Santana Krishna Garu, retired Deputy General Manager, BSNL Chennai. Sir has more than 4 decades of teaching plus industry experience in Department of Telecommunications BSNL and 3+ years of faculty exposure in NIT Nagaland and state universities that add value to the core competency in teaching technical and management subjects. He introduced innovation in industrial training through e-campus and e-learning programs in Department of Telecommunications BSNL, for which Vishisht Sanchar Seva Padak was awarded. Teaching PG students along with coursework for PhD scholars in NIT is another milestone after superannuation. His significant contributions include introducing next generation technology design for transporting high bandwidth cable TV signals across Tamil Nadu and design of BharatNet project for Tamil Nadu government. Welcome you, sir.
Thank you. Thank you very much.
Thank you, sir. Over
Can
to
I
you,
start
sir.
now?
Yes, sir.
Or you want somebody to join still?
No, sir, you can start. It's already 9:30, sir.
Okay. Good morning to all participants. It is a great pleasure to be with you this morning. And I am supposed to take tomorrow second session, and it has been just preponed. And of course, it is one side it is good for me and for you also. But only point is that this particular session has to follow the introduction of 6G, because now we are going to discuss only the research opportunities and the role of machine learning in 6G. So fundamentally, we require an exposure on the requirements of 6G. So then it becomes an important for me that I have to do some justice for foundation of 6G, and then go on for finding out the roles and then telling you the research opportunities. Okay. So no issue. Now we will start with that. I'll assume that my PowerPoint is visible to all of you, and my voice is also okay. Can I start?
Yes, sir. Yes.
Can I start? Participants, can I go ahead?
Yes, sir. Yes, sir.
Okay. Okay. So now the topic today is research opportunities and then role of machine learning in 5G. Okay. Right. Now, before going to the research opportunities, we have to first of all understand some of the nuances of 6G. And you have been already given a lot of exposure on machine learning, and I assume that you have a very good exposure on that. And you are also now for the past 1 week getting exposures about the 5G. Now I will just crisply say that take you a walkthrough on the 6G by comparing the 5G. And right from the beginning to the end, I will be discussing upon the mobile networking concept leading to 6G, and then how the mobile machine learning can fit in. So, every module we will discuss in terms of physical layer, then network layer, then we will discuss in terms of application layer, and then in each layer, what are all the various research questions are involved, and it will be very useful. The motivation part of my lecture is that for the people who are in the academic, you will have a very comfort level to understand what is happening in the industry level with respect to the 6G, and then what academia is supposed to contribute. In addition to that, people who are looking for research opportunities, we will discuss very deeply what are all the limitations of the current networks leading to 5G, and then these limitations can be broken out by introducing machine learning, and then how to take forward. And then every module end we will discuss about the research opportunities and then questions involved. And my role mainly in the motivation will be to trigger your interest and then requirements of the research opportunities by putting more and more questions. But we will not, I am not going to focus on a particular question and then go deeper into that. Okay, so we will give you a broad overview and then see what is the best research question we will be able to select if you want to pursue your career further. So at the end, I will be with you for around 90 minutes, and then at the end of the session, I hope that all of you will have a very good exposure on the fundamentals of 6G, and also how to do the stitching of machine learning opportunities into the 6G, so that you will be able to publish papers very comfortably going into a particular line of interest. So for that, right from the beginning and even to the end, I would like to emphasize that you should have a very good sound base of machine learning, and also mobile communication basic concepts, so that you will be able to take both of them together towards providing a good insight and then research case for 6G and then ML. Okay. With this motivation, now I will go to the introductory aspect of that. Okay. So right by now you have been repeatedly been exposed since yesterday that the 5G is providing a data rate. Okay. So 5G is providing you a data rate of 1 Gbps, then individual data rate, and then you have a control plane, that is latency. You are able to provide up to 10 milliseconds, and mobility is there, and so on. So now if you see the, I will take the laser pointer. If you see the 6G, you can just see that individual data rate is now around 100 Gbps, and then that is a total downlink data rate is more than 1000 Gbps. So control plane latency, you can see it is less than 1 milliseconds, and then mobility, you can go in a car, up to 1000 kilometers per second per hour, and also spectral efficiency, you see 100 bits per second per hertz, whereas in 5G it is only 30. So if you just compare, it is all leaps and bounds, the request and then imagination.
Excuse me, sir. Sir, slides not moving.
Slides
Sir.
are not moving, sir.
Slide is not visible.
Not moving.
Not moving,
Just first
sir,
slide
not
only
moving.
visible.
First
Sir.
slide only.
Now I am in second. Achha, it is not moving.
Ah,
Yes,
yes,
sir.
sir.
1 minute.
Yes, sir. Okay, sir.
Now it's okay.
Okay.
Now it is okay, no?
Okay, sir. Okay, sir.
Right. So now it is the leaps and bounds, See, the 6G is now going to provide you a sumptuous meal with respect to the mobile technology. Okay. So this is the jump. But I would like to emphasize here and then motivate you right from the beginning, warm up you with the concept of intelligentization, and then connecting heterogeneous devices. So far the 5G, we were talking about connected devices. Okay, so we were only talking about connected devices, right? Now 6G is going one step forward and then saying providing intelligence to the devices, and that is what we call intelligent, and then providing intelligentization. The moment the word intelligentization comes into the picture, automatically the artificial intelligence comes into the picture. When artificial intelligence comes into the picture, the subsets, for the artificial intelligence, these are the machine learning techniques are automatically come into the picture, and that is how we are now today. I am with you today. Okay, now another aspect is exponentially increasing of connected heterogeneous devices. So you were all getting discussed about IoT, and then machine-to-machine communication. Okay, so ultimately you are going to say that the future is going to be with device-to-device communication, and then today they say more than 50 billion devices have been connected, and then it is getting exponentially is getting increasing, and the devices are not uniform. The moment it is devices, that means they are all components of the wireless sensor networks, and then they are basically sensors, So sensors mean that is not only sensor, but they are all actuators also. Okay. So now we are going to get connected the sensor and actuators. Ultimately, the future is going to be billions and billions of devices which are going to be different manufacturers, different makes, different designs, different microcontroller architecture, different operating systems, and then miniaturized sizing, different power problems, and fairly specific to the application. And then we are going to have the division of control plane and then data plane, because now we are going to do virtualization of the network also. So in that perhaps you would have been exposed to software defined networking and network function virtualization, and then concept of the network slicing. So I'll slowly give you the basic concept. And basically I'm an industrial person, so bring all the industry ideas into side so that you can blend it with your academic and then do wonderful things. Okay, so the intelligentization and then connected heterogeneous devices are now making us possible to bring data rate of more than 1000 Gbps and latency of less than, and then when you go more than 1000 kilometers speed, then handing over, okay, all these things. Okay, and then we are going to provide virtual realities and then things like that. So the intelligentization is going to do so many things for you. So this is how we are going to take up now. Okay. So with this, then we will go deeper. When you talk about the intelligent, okay, then the main communication, the vision of 6G is the holographic communication. Okay, all of you know hologram. There, the hologram, the intelligence is put very tiny. This one. Okay, from there now we are able to take the artificial reality and then virtual reality using these high fidelity networks. Okay. And then you have the ubiquitous network. That means you will have connection everywhere, at connection at any time. Okay, here this is another important point you have to understand. The current network, you have separate network in C, you have separate network for landline, separate network for mobile with using air. Okay, now I would like to say here, if you have a mobile handset, if you take it near in a sea and then travel in a ship, you will not be able to get connected to a base station. So is it true? I think you will be able to appreciate the point, because every mobile network has to have an infrastructure, has to have a cellular coverage area. If you go inside the sea, there is no cellular coverage area beyond say 4-5 nautical miles inside the sea, and therefore there is no connectivity. So how to provide connectivity? If you, whether you are in the plane or you are in the moving up in the air or going inside the sea, then you have to provide anywhere, anytime connectivity, and that is what we call as the ubiquitous connectivity. Here the question is, can you link the infrastructure of communication, which is in the air interface, whether it is in the space, whether it is a ground level, whether it is into the sea, maybe whether it is undersea or oversea, whatever may be. Okay, that ubiquitous communication, whether it is possible, then that is possible in the 6G. We are that later slides I am going to see how that is going to be done. Okay. Now, when you provide intelligentization and actually the deep learning and then tactile internet, touch feeling of touch, feeling of hearing, okay, and telepathy, deep mind. So mind-to-mind communication. So these are all the things coming into the picture. So basically the intelligentization is now getting blended with the deep learning, then holographic communication, and then ubiquitous. Then now, if you want to go for all these things, the present communication technologies, whether they will fit in, okay, or whether they can exist without the learning techniques, okay, that is intelligent technique, is the question now. So up to 4G, up to 3G, we were not worried about the machine learning, okay. We were not worried about the artificial intelligence, okay. When it starts coming in the 4G, small things are coming. So small things, I mean, one of the examples I can give you is the Alexa. So you take your mobile phone, you simply say, get your Alexa downloader and then get it connected to a TV and then say, please connect me this particular channel or please book me a ticket. Then it analyzes your voice, understands your voice and understands what you have in your mind and by your words, and then try to say, if you say I want to book a ticket and then say to which flight and other things. And then the deep learning, that is the machine learning techniques come to the picture, and that particular application is available on the phone, and the phone is getting integrated to the internet, and then through internet and the specific application of your machine learning, you are able to use this Alexa program and then try to intelligently book the tickets and anywhere. Okay. Now, when it go to 6G and then going to connect billion number of devices, okay, it is now man interface is there. When you call about Alexa and then tell your phone and then book a ticket, or if you say, please switch off the fan, and through Alexa, if you say, that voice and goes through the sensing and then it immediately switches off the fan. Okay, when like that, billions of devices are going to be connected, you find that slowly the machine learning is creeping into the network, okay, through the applications, okay. If so, how this technology is going to get blended through machine learning and then sixth generation communicator, in how much it has come to the 5G. So 5G, you find that there is no tactile internet, then mind, okay. So these things are not there, okay. So these things, when these are all coming, then how we cannot go without machine learning. Now at this slide, you have to fix your mind that future is not without machine learning. Machine learning, I cannot talk about, I cannot simply say the word role, even when the heading given to the today's lecture, role of machine learning, I will say that the word role is not befitting to the heading. I can say indispensability of machine learning. That is how we have to go now. Because without that, the particular technology, mobile technology cannot exist. And that is the way forward we have to think, okay. So with that in mind, go a little further into that. What are all the potential key technologies? Okay. So when you want billions of devices are getting connected, when you have more ubiquitous connectivity, we want more spectrum. By this time, last 2 days, I also attended some 2, 3, 4 sessions. There we were people were explaining about you the spectrum efficiency, number of bits per second per hertz, and then you want to have a bandwidth. If so, you have to go for terahertz communication, okay. And then you have to go for visible light, okay, using the optical wire communication. So the spectrum is getting expanded, and then when you have the more and more the technologies are coming, then devices are going to be connected. Then you have to go for the concept of sensing, and then you have to go for concept of compressed sensing. So now if you see now what is the compressed sensing, it is nothing but a signal processing technique. We are getting acquiring the signals and then we are reconstructing it, okay. So to understand the linear system, and mobile system is basically a linear system, and then we have to go for the sparse theory technique and also the coding. So why do you want coding? All of you know that in mobile communication, first of all, the channel is getting attenuated, and then it is getting disturbed because of attenuation on the line, and then then we should have a very good coding technique. And then when you go increase the bandwidth, and then we want to go into decrease the latency, then very good coding techniques are required. And then you have already discussed about the MIMO and other things. We require very good large scale antenna techniques, MIMO, okay. So for all these things are there, and another very important thing is flexible spectrum. So here now basically the very main problem of a mobile communication technologies, you see that it is a spectrum. Each operator is getting 5 gigahertz or 10 gigahertz, and they have to build up more number of customers, So they have to go in for space multiplexing or the time division multiplexing, frequency division multiplexing, okay. So the spectrum becomes a very crunch, and they have to pay so much, and then you are seeing, hearing a lot of things in the public domain about the problems of the spectrum sharing. Okay, now when you want to increase the bandwidth and then provide more number of facilities, then we have to necessarily go for terahertz communication, and therefore we require the typical techniques for processing and then advanced signal processing and all. Then we must go in for all of you know simplex and duplex communication and other thing. Here we have to go in for free duplex concept. So what is a free duplex concept? So by this technology is already available, you know, uplink and then downlink. Uplink means right from the mobile phone, the user equipment towards the base station, and that is an uplink. And downlink is from the base station, the signal when it's passing through to the user equipment, then that is called the downlink. And then for a speech, you know, for a conversation, you require both uplink and downlink. And then in our normal communication, GSM technology, and then code division multiplex access, you know that uplink and downlink channels are different, and then uplink frequency is different, downlink frequency is different. Okay, so when both the frequencies are different, so you have to provide more spectrum. That is one thing. Another point, in mobile communication, in our experience, industry experience, you find that uplink and downlink will not be loaded equally, and most of the time, you know, the downlink will be more loaded and uplink will be so spare. Okay, so that is the reason where, you know, the invention of SMS technology came. Okay, so in the initial mobile communication, when it was invented, SMS was not there. Okay, because it was in the time division multiplexing, the time slots were free. Okay, the downlink time slots were, so most of the time slots were free, and the operators were not making money out of that. So therefore, the German scientists have invented, why not we use the spare time slot for sending the messages, that is 160 characters. Okay, and that is how it came. Okay, that is how here uplink content, if you say data, that is in terms of packetization. Now if you see, not only voice and uplink and downlink, both are used for data as well as voice. That is the technology for in 4G and then in the 5G also. Okay, so when you go for that, now what happens? Whenever now you log in and then put a, say, gmail.com, you just send your credentials to the server, and a very few bytes of information is being shared. And then when you download a attachment of your mail, then the downlink frequency, that is downlink channel, is getting more occupied, and then you find that uplink is free and then downlink is more loaded. Now in this case, now what happens? So that uplink and then downlink becomes asymmetric. So this we call as a asymmetric, in a normal landline technology, we call it as a asymmetric digital subscriber line. And that is why, so there are a lot of digital subscriber technology concept, both on the landline and also on the digital, the air interface. So we want to duplex, we want to full duplex. At the same time, the duplexing should be free. That means if it is possible to use both uplink and downlink, the same, you know, orthogonal frequency division multiplexing, and then see the intelligence of the speech as well as the data, and so that there will not be unfair distribution of data, both on uplink and downlink. As a company, then I'll be able to make more money and then better utilization of the data. So that is the concept of this one. So the free duplex concept is this. That means the asymmetric phenomenon of the uplink and downlink has to be broken. So that is one of the very biggest achievement. Here, to get this concept of the free duplex, we require the learning. Okay, so machine learning, that it is required. So that is where we are going to stitch. And now onwards, you can, if you have a notebook, you can go on making a note that this is the research area. Now this is one of the research area, how to provide free duplexing concept using the machine learning. Okay, and there comes in a artificial intelligence based wireless communication. And then you see now here, spatial, that is a special features, the space and ground network has to be interconnected, undersea communication has to be interconnected, wireless tactile internet is interconnected. That means in 6G communication, there is no difference. Your Wi-Fi, Bluetooth, and IoT devices, IoT network, sensor network, machine-to-machine communication network, satellite network, okay, and then undersea communication, okay, everything will become one network wherever you are. That is why we say anywhere, anytime, anything, and any amount of data which you can go, okay, and any type of not only voice, it is also data, and it is also by a tactile data, it is also by reality, data connected to reality. And also there may be requirements, special features. I just want to make a mention here. There is a requirement. So now you go for automatic metering infrastructure, IoT connected network. It is only a few bytes of, actually you find that it is only 1 byte of information will go from meter to the server which is connected to the electricity department. Okay. So then it is get your meter data of your electricity home consumption is getting updated online, and you will get a message that whether it is high consumption or low consumption, how you can manage your consumption limits, how you can economically make use of that. So all these things, intelligent management will start coming. Now, if for 1 byte of information, suppose say this with the ATM machines, you just insert your ATM card, just only 1 byte of information is getting transmitted to your server. So within a fraction of a second, your number is getting validated, and then getting handshaking, when security handshake is taking place, the value of money that you are going to take out, that is also getting validated. Okay. So here what happened, very short time interval, and then very short amount, that is very little amount of data it is going to be transmitted. Such a kind of network, present day, in 4G communication, you don't have any facility. Whether minimum, if you want, you say, I can have 250 kbps. Suppose now in my house, I have say 10 Mbps connection, fiber connection. Suppose I am using only 5 kbps per the minute, but I have to pay for 10 Mbps. So when in the case of 6G, and then you have a machine learning technology, and if the machine learning understands my behavior, I will use only 1 Mbps in a day, and that too between 10 to 11, and then do the machine learning training, and then see that only at that particular hour you try to feed only this amount of data. So this is one of the research area in the case of a special features which is not available in the 4G or the now coming to 5G also. This type of facility will not be provided now immediately. Okay, so now this is how the integration of the technology. Okay, that is the landline network. So PLM, and that is the mobile communication network. PSTN is the switching landline network, internet, and then satellite geostation network. All of them are getting integrated. That means you will get one network architecture in integrated communication. Okay, and now with the 6G challenges, only objectives. I'll just go little faster because I have a lot amount of things to tell you in the machine learning stitching and then blending of machine learning for 6G aspect. So if you have any, I don't know whether you have any doubt up to this, any messages are there. I'll check up. I think nobody has asked any doubts so far. Okay. So up to this is okay, speed is okay. Learning, India, you have any learning difficulties? Can I go at the same level?
Yes, sir. Yes, sir. You can go, sir.
Okay. Okay. Now there is a challenge. Now you take the concepts, objective of the 6G. First, first we have to talk about the radio performance. Then we have to have the connecting intelligence. I talked about the connected devices, and then talked about the intelligence. Then I also told the architecture beyond 5G and what is 6G. What are the evolution? How the network evolution is taking place. Okay. So in this orchestration, now if you see the radio performance towards this one, here the one concept is synchronization. Okay, synchronization. Mobility synchronization. Basically, if you know one type of basic synchronization is a channel synchronization. That means the base station and your mobile handset, they have to be synchronized on this time scale. Okay, so that synchronization has to take place. If it is not the synchronization take place, the clock of the base station and the clock of your mobile, they will be on a different phase difference. Okay, so if we want to have a good coverage and then you have a mobility, then you should have a synchronization. When you go towards the 6G, the synchronization is one of the very important concept, and there your machine learning is going to play a very good things. So where the machine learning can play an important role is in the MIMO and then beamforming. Okay, enabling the hardware. What are the hardware technologies we are enabling, and that I am going to tell you in the later slide. I only give you now headings and then ideas. Okay, and then what are the type of modulation and waveform where you can have the synchronization aspect, and then channel synchronization, how you are going to do that. Okay, and then here localization and then sensing. Okay, so the sensing, because the future is going to be only on the IoT devices, wireless sensor devices, which are going to be the end devices for radar, artificial reality, virtual reality, the cameras, then industries, and then robots. So the resolution for time and then velocity, in case we want to do the localization and then sensing, because 6G is going to have a very good tactile internet and then high resolution. So the localization is very important. Now current day 3G and then 4G, you can have a localization only with respect to received signal strength. So what is the received signal strength? Your mobile, when it is very near to the BTS, the power level is high. It receives the power level is very high. And then when you go towards the boundary of the coverage area, the power received is going to be very, very less. It is going to get reduced. So now what happened? The mobile handset is now talking to the BTS and periodically exchanging the values of the power level received, and then the mobile, the base station sends this information and then calculates the power level from the received signal strength, that is the power level of the signal. We are able to predict the location of the customer. Okay, so now that is not sufficient. When you go for 6G and then you are going to get connected to the Internet of Things, I want the latitude or longitude of the location, very precise location of the customer. So when you want that, when the IoT devices are going to be there in areas where there may not be even coverage, mobile coverage will not be there, whereas the wireless sensor network, through this sensing on a particular location, based on the data-centric sensing and then localization, through the gateway they send the information to the cloud servers which is connected to the mobile network. In that case, so we have the sensing and then localization is going to be very, very important. And therefore, you find in the bottom the spectrum what we are going to use is now going from from the gigahertz of 2 to 3 gigahertz is going beyond 30 gigahertz now, because we want to have more spectrum now. Okay, so this is the radio performance. So in the case of now the connecting intelligence, in the case of here, if you go through this one, so the idea is now we want to have predictive orchestration. Okay, and then we want to have network, full network has to be made programmable. Then the monitoring should be adaptive. That means the monitoring, that means there is a sensor and the network is connected into the 6G network, and then it is a camera, and then it is an artificial reality. Okay, the movement of the video has to be very clearly sensed, and then it has to send to the distant end, and there cannot be any break in the frames which is being transmitted. Okay, for that it has to be monitored. But for this, is one set of frequencies is not sufficient. One for tracking, one for sending the information that is required. Okay, so this point I will discuss later. But now you got to understand This is called adaptive monitoring. When you say the coverage is not pakka, then accordingly your algorithm has to change. There your machine learning is coming into the picture. Okay, and then data-driven optimization. This is one of the another concept. So data-driven optimization. That means when say car is moving, because unmanned aerial vehicle, unmanned platooning the vehicle, automatic driverless vehicle concept is coming in the 6G. There the data-driven. When the speed is getting increased in a car, then I require more data, and then who will monitor? Presently, there is no monitoring mechanism because the network is linear, and then there is no artificial intelligence put into that. So we require connected intelligence. As and when the driver, they increase the speed of the car is getting increased, I will be able to do intelligently, train and then find out the algorithm, and then using the machine learning techniques, I must provide connecting intelligence so that I will be able to increase the data. Okay, so and another concept is the end-to-end seamless integration. End-to-end seamless integration means one side there will be wireless sensor network, another side it may be satellite network. So there the server may be there, and the end-to-end network IoT device will be there on the sea. So the satellite, latency is more. The sea, the connectivity is very less. But now, in present day, what we do, we build Internet of Things using the sensor network, then build up with a landline network, and then provide interface with a mobile network, and then get it connected to the satellite network, and then provide a matching interface for all these network to have a seamless integration between the device and to the satellite, the connectivity to the satellite. But that will not work, because you will have more latency, but I want latency less than that, okay, for critical surgeries and other things. So there it comes a concept of end-to-end seamless integration. Okay, so here we have to go deeper into the connected intelligence. Okay, now comes a idea of network evolution and then expansion. Why? Okay, so what are the different type of network is there? So we have 5G. You have learned, I think, machine type communication, ultra reliable, low latency communication. So these are the concepts you have learned. Okay, but if now we want something beyond ultra reliable, low latency communication. Okay, if you see now here they are using the concept of digital twin. Digital twin. The concept of digital twin is one of the concepts which is going to be blended with the machine learning. You can now make note of it. Here in this case, if you want to have digital twin concept, so now you take a machine-to-machine communication in the industrial robots, and if you want to provide a particular application for industry, and then that is a physical entity. For the physical entity, you want to provide interfaces and then machine learning interface. Okay, then that is called a digital side. The physical side and then digital side, they are now together. They are like a twin. So both are getting interrelated. So this concept is called a digital twin, and that is going to be integrated into the intelligent connected devices. Okay, so and you want to have centralized or distributed artificial intelligence enabled. That means you are connecting the robots for different industries and different locations, and then you can provide a central intelligence, artificial intelligence, just like in a smart grid. Okay, and then there is a windmill farm is there. The motor getting burned. The central artificial agency get the input, then find out if this is a summer reason, this is a temperature is very high, the motor reached the temperature of 33 degrees, the motor has got a pre-history of this time, it is likely to burn. So like that you can interpret the value for the wind farm turbine of that motor, what it is rotating the blades, and then give a centralized AI enabler to the distributor. That we are going to see the cloud radio access networks. Okay, human machine interface, how they are going to interface. All these going to get connected to the network, and the network is going to get evolved. So 3G we were having only mobile communication, they are not getting integrated except voice. In 4G also you find the landline communication and mobile, they are not getting integrated. You cannot keep it as one network. Whereas the 5G communication, you find that our landline network, our mobile network, and also the Wi-Fi network, they are getting integrated. Okay, to some extent, the IoT devices are going to get integrated. In the 6G, not only the device to device, okay, you have to get any enablers through artificial intelligence, using the digital concept, any human machine interface, all of them are going to be connected, and then network is going to get expanded, and then you will get only integrated network, and that is the way we are going, network evolution, and then artificial intelligence is coming into play in a very big way. Okay, now you see now this is the 6G network in which you will have the wireless access, and the wireless access, when it is getting connected to this one, either you can have a distributed access or you can straight away connect it to the central unit using a front hall, and then these central units are connected to the internet through the backhaul. So you have the front hall network and then backhaul network, they are all through the fiber interface, and then these dotted lines or the air interface, there you have the wireless access. The wireless vehicles are fixed in your houses and other thing, maybe pad, iPad, or the mobile equipment. You have the user equipment, and then you are going to have access network using the front hall and the back hall, and then you have the central office, and then you have the internet. Now, just to see now how artificial intelligence is going to fit in. Okay, now when we want to discuss artificial intelligence, this 6G network, you have to think of only now OSI layers. When you think of OSI layers, then you have the physical layer and MAC layer, then you have the network layer, and then basically you have the application layer. These are the three layers, very important, which you have to conceptually develop. Now, in this physical and the MAC layer, so what are the jobs we do? So we want the bandwidth has to be allocated. That means for that we require resources, and then we have to do the scheduling, whether the bandwidth, at what time the bandwidth has to be allocated. Now presently your mobile is there, you just switch on, whether you make a call or not, okay, there is a that is getting the, now can you make, so when you want to go to make up sleep, then you have to understand my behavior, when we will use, when I will not use. Now machine learning comes to the picture. This is one of the research area in your 6G, where you can develop algorithms and then say whether the mobile phone itself can go for sleep whenever you don't require that. Okay, whether any channel, broadcast channel, paging channel has to be allotted permanently to you or not. Only when you just touch the phone, then your paging channel is allotted. That is sufficient. That is not there now. So whether that can be done, that is one of the research area. Okay. Then once you say I want to get attached to the network, then the mobile phone has to say I am there in your network. Please attach me. Then the node, which is going to get connected in the front hall or through the wireless access, the access point or whatever it is, it has to give you a uplink. So okay, I'll give you a channel. Please get me connected. So these things, channel has to be decoded, the symbol has to be detected, and then what type of a channel? Is it a mobile phone? Are you going to do get it connected and then do the video calling, or whether it is an IoT device, or whether it is only automatic metering infrastructure or ATM, where I require only 1 bit or 2 bit of information. So this channel estimation has to be required. Now presently we don't have. For ATM machines, we don't have machine learning algorithm. What is the amount of bandwidth is to be allotted? So in our industry, what we do, if we say ATM, we provide a bandwidth at an approximate requirement. Whether you use it or not, we will bill it, and then you have to pay for it. Okay. So in the artificial intelligence, in the physical layer and then MAC layer, plays a very important role in channel estimation, symbol detection, and then channel decoding, and then so on. Okay. So this artificial intelligence network, you have the input and output, you have the hidden network. Okay. So these things I am not going very deeper into that because already you are done. Now my job is now how to get yourself understanding the basics of stitching these ideas to the mobile concepts, okay, network concept. In the network layer, I want to give you an idea how the network planning has to be done, then how network routing has to be done, and then management. Okay, all these things have to be done. So in this physical and then MAC layer, we have to use the deep learning and algorithm. Because we want to have allocate the resource. I already told you the idea for an ATM. What is the resource to be allocated? The moment ATM is not used there, how to make it to go for a sleeping mode, and then what is the power required to be allotted? Here, the deep learning can optimize. So you have to think how, what are the areas in the 6G, how the deep learning can do that, and that we have to go for a particular research algorithm, do the problem statement, and then what is the present state research work, literacy survey has to be done, and then how to go further. So in the case of now, furthermore, we have to discuss about machine learning algorithm, which is going to help in channel estimation and also the user selection. We will see now how that is going to be done. Okay, so in the case of 6G, so the concept 5G, it is enhanced mobile broadband, ultra reliable low latency communication, machine type communication, massive machine type communication. Okay, so EMBB, URL LLC, TC. This is what we have learned. We are going beyond that. Okay, so in 6G, we are going to have computer oriented communication and then contextually agile EMBB. It is not merely enhanced mobile broadband, it is contextually agile enhanced mobile broadband. So what is contextually agile mobile broadband? Okay, so I am moving in a car, I am now making I am just trying to make a video call. It is a context, and the context is agile. At that time being, I require minimum 2 Mbps, this one. My 6G network will sense that at that point of time, it will alert me a slice, okay, network slice, and that network slice will provide me 2 MB. The moment I disconnect and get out from the car, then the contextually agile, okay, the communication, it will provide EMBB services, not 2 MB, only what is required. It may be even less, it will provide that one. So this is called a contextually agile, okay, variable. And then event driven ultra reliable communication. So now this is now a doctor through a video on his iPad doing surgery. It is an event, and that is going to be defined. It is a critical, ultra reliable, ultra. That means I want to provide less than 1 milliseconds latency. If that latency has to be provided, end to end, I have to provide a network slice. Okay. So using the network function virtualization, using the say concept, that means presently even the up to 4G you don't have the network function virtualization. It is slowly coming into the picture. Network function virtualization is now there in the 5G. If you want to provide event driven ultra reliable communication, so that is not there. So when you have a centralized control plane and then a data plane, probably we will be knowing that. Yeah, of course, it is a different subject. In that, I'll give you the concept as a mobile communication man. Now you have to very clearly have a basic ideas on the central control plane, data plane in the software defined networking. When you have a data plane, and the data plane says 1 Mbps network slice for the particular doctor who is doing the surgery. He end to end, please remember the point, end to end, right from the surgery table, okay, yeah, till the place where the people are watching, the other doctor who is giving the instruction, it is an end to end pipe is created. Okay. Now, presently, if you want to, any of you from your mobile, can you do that the configuration for that particular time? I want the pipe to be done. This is so in the ultra reliable low latency communication, it is we are able to do that one. And then computer oriented communication, we will be able to provide quality of service. So what is the quality of service? Okay. So now the classical quality of service is 99.9. Suppose if now 100 hours you are taking a service from my operator, I will be able to provide for out of 100 hours, 99.9 hours I will be able to provide uptime. 0.1 hour it is only given to the God. You cannot question me. That is the quality of service I am providing. Suppose now there are technologies in 5G, you will be able to provide up to 4G, 4 nines, 99.49, 99.59. Can you provide 99.5 5 nines? That means after decimal 5 nines. That means almost equal to 100 hours. I am providing a service, quality of service, 100 hours. It will not fail, and that bandwidth I am providing, and that is configurable by the client and configurable by the IoT device. Okay, right? This is called a computation-oriented communication. That is now, it is just like that. If a president comes to the picture, the entire road, it is getting blocked by the police people, and then say nobody else can pass through. So this is called a quality of service for the particular service. Okay. So the police come into the picture and then block the road. But here the path, the data path, what you want can be defined and then critically configured by the customer using this computer-oriented communication. So in the challenges of the 6G, end-to-end qualified service provision using the network slice by the concepts of the service provisions available, contextually agile EMBB, and then event-driven ultra-reliable communication, and then computer-oriented communication. Okay, right? So these are all now you find intelligentization has come, and then we want heterogeneous network has to be communicated, and then we want network slices, and then quality of service. So these are the challenges now. Machine learning naturally is now coming into the picture. Without the machine learning, we cannot go. So I will not call it as a necessity. ML is a must for 6G. ML is going to play a very important role on 6G. So we will now go through the steps. If you want machine learning for 6G, I have to classify under 3 classification and then study how further it can be done. Okay. So is it clear up to this? You have any doubt? Any message on your this one? I think nobody has got a message. And then can I assume now things are clear? Can I go further?
Yes, sir. Yes, sir. Yes, sir. Clear, sir.
So I think I have spent more time on these basic things. And is it okay? My speed and everything okay? You are able to understand?
Okay, sir. We are able to understand, sir. Nice, sir.
Okay. Okay. So now challenges from the future ML. One is the communication, another is the learning model, another is the computing. Okay. So these 3 things you will see. Communication, I have already discussed that. This is a heterogeneous communication. Okay. The existing configuration, I will not be able to do adapting. That means when I want to provide bandwidth of required this one, I will not be able to adapt. Okay. So we require a communication system with ML where the heterogeneous techniques has to adapt the configuration and also the topology. Topology means whether it is IoT device, whether it is a handheld device, it has to adapt. Okay. So that is the requirement for ML in the communication system. And then the ML will have a different type of learning model. There are a lot of different type of learning models. And for the purpose of time, I have omitted the introduction, that is a role of ML. See, different ML things I wanted to discuss, but I will not be able to do that. I will skip that. Offline, if you want, I will share that is one. Okay. So now I will just make a mention about those things. Okay. So in the learning model, okay, my problem is the model learning efficiency. My focus is the parameter optimization and then model optimization. Parameter optimization is the latency is one of the parameter, end-to-end design is one of the parameter, bandwidth allocation is the parameter, synchronization is the parameter. Okay, so these are the parameters you have to keep in mind where ML can creep into that. Okay, next is overhead. What is the cost? So you cannot simply do that, and then overnight the entire 6G cannot be brought under ML. There are different type of application. All the application has to be integrated. That is why standard models, is not getting evolved over a period. So that is why they have started. Even ML specification is being designed. These standards have came into the picture. Okay, and then we require learning models with self-adaptive for changing topology. That means whether the customer is there in a satellite, whether the customer is moving in a car, whether the customer is in the wireless with the access point. So the topology is changing. Whether the learning model has to adapt. So this is one question. This is one of the challenge. Okay, and then data set. So data set, amount of data set, quantum of data set is getting developed, getting generated is massive in a mobile communication system. The learning model should adopt the open data set model. Whether the open data set is available, because it is all with the operators, so operator will not share. This is another area difficult. So the privacy problem is one of the very important issue, and that you have to understand. Then we require a very good computing system. Okay, so for the computing system, now you have understood there is a massive data set, and then machine learning slowly coming to the picture. The massive data has to be learned. How that is going to be done? Okay, so this problem. So when you have a computing system, already cloud has into the picture, fog and then edge computing system has come to the picture. Okay, now I assume that you all know, very familiar with mobile edge computing, mobile fog computing, and mobile cloud computing. Now in all these cloud computing situation, the computation resources required are different. That means if you do the edge, suppose now you have the wireless sensor network getting the sensor data, and that has to be, suppose now in a forest sensor, and that has to be processed at the edge of the wireless sensor network itself, and then you try to use the map reduce and those type of concepts, and then reduce the quantum of data where there are duplicates, where unwanted data, all these things are there. That we call as the edge computing. Now at this point, whether you can introduce a machine learning, yes, that means there may be irrelevant data, unwanted data, and then it may be raining, and at the time you may get that forest fire sensor data, temperature data in terms of burning category. Say, let us say if it is 35 degrees centigrade, 35 degrees centigrade, and you get this one is heavily raining, and you get this data, then you have to discard it. Okay, so who senses, who computes, and then who does the learning by this one? And here the computing system plays a very important role for, and if it gets combined with this machine learning technology and mobile, that is the mobile communication, linear, the mathematical models will not work. Okay, so if it is not going to be linear and mathematical models are not going to work in our traditional technological scenario, then we must have experiment for conducting machine learning based algorithms and then doing computation using that. Therefore, you have to study this. If you want to do the research, you have to manage that in this type of categories. Whether you are doing research in the computing system area, whether you want to do research in the learning system area or in the communication system area, is a point you have to try to understand. Now, with respect to machine learning, what are the very important areas of research where you have to start studying that? I have now categorized some 10 basic areas. You can see, I can give the reference of these papers are also to you. So you want to do challenges with using the machine learning. The machine learning has got a role in end-to-end service provision. I have already discussed what is the end-to-end service provision, and then physical layer, Mac layer, and then application layer. In each layer, machine learning has got a very important role. And then dynamic online learning with proactive exploration. Now, artificial reality, okay, virtual reality. So this is the reality video transmission. You have to find online. You have to find out whether there is a break in the frames which is being received. So for that, you require proactive exploration, the learning is required. Whether there is really virtual reality video which is being presented, is there any break in the frames? For that you have to get the feedback, and then in the feedback you have to do the learning, training, and then try to understand if it is there is a break, whether the distant end customer, whether he is really feeling that there is a break in the, whether he feels real scenario with respect to the original video which is being transmitted. Okay, so this is the dynamic on-learning learning with the proactive exploration. Whether you want to do that distributed or centralized, that means whether you want to do processing in the edge computing or in the fog computing, or you want to do that in the cloud computing. Suppose now I tell you, so now the system has done content delivery network is there, wherein the television channel people are seeing in a particular location. Now the television channels have started coming in your mobile itself. If you are seeing in a mobile channel your television, suppose now Olympic is there in one particular street, so 100 people are seeing the same Olympic in their mobile phone. This is the situation. Okay. Now content delivery, when it is broadcast, say from Hyderabad, and then it comes to Vijayawada, in one particular street 200 people are seeing the video. Now what will be your design? Present design is the packets pertaining to the video for all the 100 customers will come independently in a different channel from Hyderabad server to all the people in a particular location in your street. That means there is a congestion in the channel. Unnecessarily your multiple packets are getting repeated for the customers. Now we will use the machine learning and then find out in a particular locality these people require the same picture, the same video. Why do you transmit from Hyderabad to video? No, don't do that. Get one packet to the edge of the node. Okay, base station BTS in the conventional technology, node B in the 5G or G node B in the 5G or the 6G parlance. Then for the node, you provide a cache server in the edge, and then see that the packets are getting repeated for the 100 customers. So this is concept of the decentralized and the distributed concept. And then whether you are able to do the global intelligence or the local intelligence. This point I am coming later. I'll just introduce that. For the time being, you just to understand that there is a provision for scalability of the global intelligence. The global scalability of the global intelligence means if there are 10 to 15 customers are roaming in a BTS area and they are moving out of the BTS area, this BTS area, the local intelligence of this using machine learning technique, this handsets, user equipments will get the intelligence and then transmit to the mobile base, that is eNode B, and that will give the nearby node and say that this particular customer is moving towards your area only. Definitely he moves because he has got a habit of coming from this point to that point. Okay, that is my intelligence, and then this is my global intelligence, and the information given by his neighbors and by him is the local intelligence. From the local intelligence, I had done the machine learning analogy and then derived a global intelligence. My global intelligence says that he is coming to eNode B2, which is very near to that, and be ready with the resources and other thing. Therefore, the real picture, the video, these handover problems will not be there, and that plays the scalability and the local intelligence. So you can increase the learning efficiency. I told you data set the generation. Massive data set is going to be generated, and then overhead. When you use the intelligence, when you use artificial intelligence, machine learning, the computation overhead is going to increase. When it goes, you are going to manage it. Okay, then you have seen that whether providing massive machine learning intelligence is feasible, and then when you do the standardization, what are the things you are going to encounter? Now you please note that these are all the 10 basic points for the machine learning, the role of machine learning when you want to do research in the role of machine learning to 6G. Okay, and then when these things are coming into the picture, so now the problem is when you take the physical layer, then the network layer, physical layer, okay, then you come to application layer, you find that in the physical layer, adaptive configuration, the configuration adapted. What type of network, what type of configuration is required? When you come to the network layer, what is the type of radio required? Whether it is what type of frequency is being used, how much bandwidth has to be allotted. Okay, so then what is the media, the rate of data which is to be sent? So that has to be controlled. So in the machine learning, for 6G, when you want to do the research, then you have to think about adaptive configuration, radio research scheduling, and the resource research scheduling, and the network traffic control. How much amount of the traffic has to be given. Okay, and then here, if you come the other side, whether in the application layer, the computed information, how you are going to offload, how you are going to predict the traffic. I told you, when the user with the mobile is moving around, and then I will be able to predict user his behavior and previous history. Definitely he will move towards this one. Okay, let us say now a car moving in the highway, and he has programmed now, he is going from Hyderabad to Vijayawada such a location of this one. The moment the network node in the 6G knows his destination, knows his route, now the machine learning algorithm understands the prediction. Okay, this is the route is going, this is the network is going to travel. So immediately in the cluster, what are the nodes is going to likely to pass through, and then what is the traffic is going to do. Immediately what are the channels, automatically the machine learning algorithm, you predetermine, you fix it, and then you provide a route to him. So that is the way you are going to do machine learning algorithm in the 6G. For that, we basically require the data link layer, channel method, traffic clustering in the network layer, and then you have to predict the transport in the traffic layer, and then you have to offload the computing, this one. Okay. Next is the role of ML in the 6G. If you take the physical layer, I have to talk about this end-to-end modeling using the online learning. When you take a MAC layer, okay, autonomous decision has to be taken. For that, predictive resource allocation, and then federated eco-state learning. So these are all the concepts I have just explained you one by one. Okay, and then network layer, quality of service has to be done, and then application and the transport layer, ML as a service we have to start providing, because we have to put the service, holography, autonomous driving, and massive robots. They require different type of quality of service. Okay, so in other words, so far the network, mobile comm network up to 4G and then even 5G, we were not driving towards client-centric networking. Client-centric network means the moment I get a service operator, whomever I want. Suppose now you take a SIM from BSNL, you cannot get an ATAL service. Now in the 6G, irrespective of the provider who provides a SIM, you will be able to get connectivity for a particular video conference. You can go for Airtel. For mobile video call, mobile voice call, you can go for Vodafone. If you want to provide a connectivity to a doctor with respect to your body area network which is getting connected to your mobile phone, you can go via BSNL. Irrespective of the SIM card, please remember, SIM card is a common. In the application level, I am planning. Client-centric network, I am planning. If I want 5 gigabits of bandwidth, I will say I am ready to play. Immediately, amount will be deducted and I will be getting connected. So this is called opportunities networking, and then client-centric networking. So this is the role of ML is going to provide this support. Okay. So more intelligent connected object I am going to do. Okay. So wireless communication network is no longer is for voice or video. This is going to provide data based on your past experience and then knowledge and experience. Larger and larger amount of data that is going to be transported. So machine learning is going to represent basic functionality and then guarantee wireless networks. But if you go on providing interoperability, repeatability, generalization, and then providing network, ultimately this is going to provide overhead for network. If you increase the training accuracy using the mobile, and then the network overload will increase. So you must have a balance. If you want to do the feasibility of the machine learning in network, you should have training accuracy and then network overhead. Increase training accuracy, this will go up. If you increase this will go down, accuracy will go down. So you have to do the strike a balance in between. Okay. So if you see the research opportunities in general overview, okay. So I will now sum up now. ML method, what are the ML method going to have a major role? Okay, in 6G. Okay, what is the areas in which 6G is going to use deep learning, which we have discussed now, different areas. Deep reinforcement learning, what are the components of automation in 6G network I am going to make use of? Okay, open data access, if it is brought together, what type of problems we will face mobile network operator infrastructure, because operator will not share this data. And then what are all the efficient model which you are going to be transferred in the resource constrained platform? Okay, how you are going to couple it? Okay, how are you going to dynamically select application and then platform dependent models? Okay, application, every application is different and we require different platforms. That means for IoT, one bit you want less than 1 millisecond latency. Okay, critical, time critical. At the same time, I make a video call, that much of the critical latency I don't require. Therefore, if you want to use supervised learning or unsupervised learning, reinforced learning, deep learning, I will explain you about the, probably you will know federated learning. I will tell you now how it is getting fitted in this. And then reproduced kernel helped space concepts and then probabilistic methods, where you are going to make use. So these are all the question marks here in the research areas when we want to go use these research opportunities. Okay, now I will go to the MAC, that is a physical layer. Before going to the physical layer, up to this, do you have any doubt? And some questions have come. Yeah, I think nobody has got any questions till now. Okay. Is it okay up to this? Can I go further? Another only 10 minutes, I think I will be able to, I will not be able to complete fully. Okay, ML at physical layer, I will go a little faster. Okay, now we will talk about the ML at physical layer. Physical layer, okay. Normally in our wireless communication, all the models are the mathematical models, okay. So they have a non-linear factors wherever the physical models are concerned, okay. Now when we want to have 6G wireless concern, then we want to integrate ML into the physical layer, okay. Now a lot of research has been conducted in the recent period. In that you want to use the ML to replace, okay. Many problems are getting not well solved so far. So for example, if you take one problem is uplink and downlink reciprocity in frequency division duplexing, okay. So what is a reciprocity in the frequency division duplexing? That means there is an uplink and there is a downlink. So you use a frequency band in the uplink and then you use a frequency band in the another downlink, okay. So when you use these two frequencies, okay, this is called the reciprocity, okay. Now there is an interference because the bandwidth, you take the adjacent bandwidth, there is an interference between these two, okay, because the power used in the uplink and downlink are different. Normally in the downlink the power is very loose, the high power in the uplink and the low power in the downlink. There are two parameters, functions, one is frequency, another is the power. So in this is called the uplink downlink reciprocity, okay. When can we find out in the normally thing, you cannot find out the interference, okay. and then you cannot do the mitigation. Okay, and then you see how channel can be built. You know, the prediction. If these problems are occurring, the reciprocity, the channel prediction has to be considered. This is one of the problems which is existing in the current communication system in the models because of this lack of accuracy and the non-linearity. The uplink, downlink, reciprocity in the, FDD, okay, frequency duplexing is one of the areas in the physical layer. You can note it down, okay. And then in the second level, in the traditional design, okay, it is a based on only a linear model. In the linear model, what happens? So we want to do the ML integration, okay. When you want to do the ML integration, the decoding, modulation, and waveform, we always do in the traditional design, we do separately. So channel decoding, channel modulation, and this one we do. But you want to do end to end and together, it is very complex. Okay, for that we can use the ML. So a near optimal end to end mapping, which can be done using the machine learning in the physical layer. Okay, so that will be the merit of the future study. So this decoding, modulation, and then design of the waveform in the physical layer is one of the area for research. And then you take the fourth point is the integration of ML. Okay, integration of ML is the fourth level at the existing modular based methods. In the traditional method, what we are doing, okay, there are inherent defects. Even you take a 4G or 5G, when you design the ML, there are a huge training data. Either they get underfitted or they get overfitted, or there is a slow convergence models. So when you go for the intelligentization of the model, the design process of the model, when we have to look at these model-based methods for the integration of the method, you have to look at these underfitting and the overfitting of the training data. That is one of the very important area in the physical layer. Okay, and these problems in the physical layer will benefit if you use the ML. Okay, when you go for further research areas in the physical layer, so we will just think in terms of channel coding, then synchronization, positioning, and then channel estimation with respect to 6G, and then arrive at the concepts of what are the areas in which you can do the research. If you do the channel coding, okay, wireless channel has got imperfections. Okay, wireless channel, when you why we do the coding? When the signals have to be transmitted, they have to be modulated. When you do modulation, and the coding process is coming to the picture. When you do the coding, because of the imperfection in the channel, errors are occurring. Okay, right. Now, to overcome this, if you want to use ML in this channel coding, then the concept is, okay, I use the ML. When you machine learning algorithm, when you use the machine learning algorithm, we want to do the training. When you do the training, the number of codes, that bits is getting increased. When it is getting increased, the latency is getting increased. When the latency is getting increased, then again you get a problem in the channel coding when you use the ML algorithm, because I want more latency has to be decreased when you do the coding and then decoding process. Now you have to look at the methodologies, whether you can do the rapid coding. When you do the rapid coding, then you use the assumption of number of bits. When you do the code word lengths for doing the deep learning training, we want to provide deep learning, and then we want to provide training. The code word length is getting increased. Okay, and you have to look at that area when you do the channel coding and using the deep learning techniques. Okay, so when I use the deep learning techniques using the code words, okay, the code word length naturally increases when you use the deep learning technique. The code word length is increasing from 2n to 2n cases if you want to learn, because we want more data to be done. And then Because of that, the latency is getting increased. So we have to do. There are several attempts have been made to overcome the problem in the learning technologies. They go towards the zero code words. Okay. So when you do the code wording, there is a coding algorithm using the deep learning technique. So the computational complexity affects the time spent in the decoding, and that has to be looked into. Okay. So the time spent for decoding has to be looked into in the channel coding when you go for deep learning technique in the physical layer using the machine learning algorithm. Okay. The next concept is the synchronization. Synchronization, when we in the 5G knee radio, in the synchronization, you use this carrier frequency offset. Okay. What is the carrier frequency offset? So when you use the uplink, then you have the UE in the uplink frequency you are using. Let us say you are using the frequency F1, and then you use the E node B. Okay. That is the BTS, and then here this is the receiver. Okay, this is the transmitter. Okay, the transmitter frequency, when it receives receiver, it gets attenuated. Okay, and then the same frequency, if you oscillator of the receiver has to be tuned. The frequency of the oscillator receiver and the frequency transmitted, if they are not on the same time domain, then we call it as a carrier frequency offset. In the carrier, highest carrier frequency offset environment, if your mobile is moving in the fastest way, say in a car and all, so there will be worst radio channel environment. Okay, so for that we require synchronization. So the synchronization we have to achieve the accuracy. For that we have to use the ML, right? So if you try to achieve the synchronization and the carrier frequency offset, you try to achieve, towards that you can find out the sampling time offset, sampling frequency offset of the transmitter and the receiver. Okay, so using the detection of the signal detection by decoding, okay, for that you are using the autoencoder based deep learning neural network. Okay, so these things you already learned, autoencoder using the deep learning neural network. So we will be able to achieve the synchronization of the signal as a reference receiver and as a reference, and you are end to end you are able to do the synchronization for that. So at the ML level, the synchronization is doing this job. Okay, then in physical layer, positioning is coming into the picture. Normally here we use the near line of offset and then received signal strength state information. You use the channel state information using the received signal state indicator. By that you are able to provide, and I have already discussed that we are not able to provide positions exactly. We are only providing the coverage area in the 3G, and then to some extent better positioning technologies in the 4G and all. Okay, in the 5G exact positioning, because the devices are coming to the picture, and that the significant positioning errors has to be removed. For that we provide deep neural network using ML methods. Okay. So how that is done? Okay. So now in a customer moving from one place to another place, the deep neural network using the ML algorithms, you are able to find out RSS, whether it is a received signal strength is missing, is available, and to what extent it is missing. Okay, and then find out what is the power level of the signal from the UE equipment and also E node B side, and then it will not be the same. The performance will not be the same in space A and the space B. And then you have to provide massive data for the people who are moving from place to place, and then try to get the data, and then try to do the training, and then find out the positioning values. So the performance difference and the response, okay, for the deep learning based location level technology, okay, from the experiment and the actual environment. So I have done the deep learning training, and then my equipment is able to understand. So in phase A, whether the received signal strength experimental information, what is the value, and then how it can be compared with the actual environment, and then say predict where the customer is moving, where the IoT devices are there, and that can be analyzed during the research. So the positioning methods, okay, and then channel estimation. So we use the linear mean minimum mean square error methodology to obtain optimal passage in the channel. Channel is linear or the stationary. So the real channels may be non-linear or may be non-stationary. We use the deep learning techniques, okay, using the channel estimation, okay, by using these training methods in spite of the complicated channel environment, okay. So the channel estimation method, we are using the equalization by using by realizing this single neural network, okay. So the channel estimation using the deep neural network, you can be trained offline, and then you require a massive training data for a long training sequence, and then if there are mismatch in the real channel and also the training channel, that can be used for estimation the performance degradation. In future research, it can be online training, okay, by using the training data sets matching the real world channels as well as the future promising approach for the future research. Then comes is beam forming. Already you day before yesterday you have done this beam forming technique. The using MIMO, we are using the beam forming. How you can the beam can be focused on a particular customer. Okay, so now you see here the beam forming technique, the structural information. Now the beam forming is coming from the handset. It is the beams are coming from this network, antenna to this network and also to this network. And here this beam forming is say it need not go there, and the traffic is blocked. Okay, here the traffic, because it is blocked, the machine learning says you go via this. Normally, the if the beam forming technique ML algorithm is not there, if the beam forming is going from here to here, and then it say it does not know it is blocked, and then it has no intelligence, it has to be rerouted. The rerouting intelligence is not there in the antenna. Okay, the same way in the cell assessment, adjacent channel cell assessment. Suppose now this mobile is there, and this antenna is doing the servicing, and here this service is there, the beam is focused here, and ultimately the power level is more. Okay, this power levels from the beam forming can be received and then sent to the machine learning algorithm, and it can find out which beam has got the most strength, and then it can order the antenna to go and then get hooked to the particular set. Okay, and then you find that here there are so many customers, they are not fed by any recent antennas, and then this directionally MIMO system providing a beam, providing more power and more cover to the people who are in the same in a particular area. Okay, also the beam forming access in motion or in the move, providing a broadband connectivity. So here the particular customer is moving in a train in a very fast way, and then for him we are providing a beam, and then that intelligence is connected centrally, and then it is providing a radio channel based on the ML. Okay, so at this level beam forming, it is provided, we are able to capture structural information of a radio channels and to the neighboring base station. Okay, so using by MIMO, the MIMO provides the beam forming technology. The beam forming you can provide intelligent using the machine learning technology, more specifically deep learning. Okay, by this we are able to provide dedicated hardware, and then these antennas are able to adapt to the requirement of the customer of the neighboring base station, and then they are able to provide appropriate power and then emission to them. Okay, So now I think I'll be able to complete only the physical layer. Okay. So now what are all the research areas in the physical layer? What are the problems in the physical layer which can be solved by ML? Is there an end-to-end communication which can be provided by deep learning? How deep learning can optimize the physical layer? What are all the implementation issues of ML methods in physical layer? How deep learning can provide optimization for providing deep layer real data? I told you that beamforming, and then how deep learning based physical layer optimization can perform under imperfect channel state information. I told you, that is ML can get the information about the channel state information. How deep learning based physical layer optimization can combine intelligence in the upper layers, and then how training workload of deep learning model for physical layer optimization can be reduced by recent advances in deep learning such as domain adaptation. Okay, transfer learning. That means in one tower area, one node B area, the intelligence captured can be shared by the adjacent nodes. So that is a transfer learning. How can training data can be reduced by applying advances of generative adversarial network? So generative GAN network, this is another new area, GAN network area, provide to generate artificial data in the physical network. That means, so the adversarial network collects the information. That means if this is not happening, what we can do? If the signal level is getting reduced continuously, what to do? If signal level is getting aberrated continuously, what to do? And that is information is taken to build up the intelligence. So this is called adversarial network. Provide inputs of situations. What will happen if this is going to be very adverse in the output? That type of output is collected, that is provided as input. Okay, that is called a GAN network. In that GAN network, these inputs will be taken and then the data will be trained to improve the network in the adverse situations. So that is a GAN network, how the data is getting artificially generated, the advances made to train the data. So these are the some of the research areas in the adversarial GAN networks. I think now the time is 11:02. I think of course I have the Mac layer and then application layer. So another 30-40 slides I will try to share people whoever is in need of it. So at this point I will stop because 11, I think my time given to me is 11. I stop here with this what are research opportunities in the physical layer. So if anybody having any doubts or few doubts, I will clarify. Otherwise we can get connected to the offline, and also the other this one slides, for that, up to 105 slides are there, and then these information study I made from the research references, the research papers, whatever I have taken here, the references I have given. You can further go into that, these research papers on these references I have given. So with this I will stop here. Any doubt? Now it will open now for 5 minutes. Anybody have any doubts, madam? I can answer now. It is already 11:03. I think I am supposed to finish. If you say I have some more time, then I can continue also. Anyway, left to the organizers. Yeah, anybody having any doubt, please ask me.
Sir, good morning, sir. Sir, one asked doubt, sir. Please show last before slide.
Last
sir,
before.
Srinivasrao, sir, can you please?
One minute. Last before.
I shared mic also. Srinivasrao, sir, please.
One minute. Last before means this one, No, not this. For me, the last.
Sir, references, sir. They are asking about references, sir. References.
Acha, you want references,
Yes,
one
sir.
of
The references slides.
One minute. The research paper reference, I will
Revised
show you.
paper.
yes, sir. This one is.
Reference. This one,
Yes, sir.
I have the copy. I can share you also. People, you need not make an effort to note down.
Okay, sir.
I have the research paper, soft copy with me.
Okay, sir.
Okay.
Thank you, sir.
So I have the soft copy with me. Whoever wants, you can. I have given my mail ID. You can note down. I will share with you. No problem.
Okay, sir. Thank you, sir.
I have a lot of collections on that 6G network exclusively, and then another 50 slides I could not connect because I have around 100 slides. Because the first 20 minutes I spent on 6G, because this is supposed to be done tomorrow. I felt that you would have become expert in 6G. I can start from the machine learning, that is problem portion onwards, but I could not do so. Whatever it is, we can get connected. Whatever you want, I will share you. This is a slide for references. I have a lot of references, other references also. Okay.
Yes, sir. Thank you, sir. Thank you very much, sir.
Now, any other questions?
I think no questions, sir.
You are noted down my this one, no doubt. I'm wondering
Noted down, sir.
whether all of you are comfortable, understood something.
So someone is asking doubts, sir.
Tell me.
Please ask now. Any doubts? Please ask now only.
Hello, sir.
Yes.
Madam, please.
Sir.
Yes, ma'am.
Sir, actually, I'm working on channel coding, sir.
Okay.
Course I'm working, sir.
Okay.
Sir, from your presentation, I understood that we can apply deep learning techniques in channel coding, sir.
Yes, definitely, madam. Very good. You understood very nicely.
Yes, sir. So, shall I move to learn deep learning techniques and
Definitely.
sir, it will be useful for me, sir.
Definitely, madam. You please note down my mail ID.
Now
I will show my mail ID slide now. You please note down. I have collected a lot of some papers also on that. Okay.
Sir.
So I have an industry background, very good background. So I will try to help you, and then first you have to which portion of channel coding you want to take up. You have to decide that, and then 6G technology portion, the channel coding portion, and then connected deep learning portion. Both you have to decide first. Then you have to start understanding literature review. Then we have to stop and then attacking on that. So first now channel coding portion, what has been done in 5G, what has been done in 6G. So this whatever paper I referred, the authors, I think more than 10 to 15 authors are there for that. Okay, each one of them discussed very deeply into that. Okay, so we will get connected. So now no problem. I will show my that is mail ID now in my last slide. So you can make note now. My mail ID I have given now there.
Yes, sir. Noting down, sir. Thank you, sir.
Whether the presentation was useful?
Very much useful, sir. It is based to further research for many of us, for faculty and the students also. It will be great exposure.
I need one more session. If tomorrow any slot is vacant also, please tell me. I have left physical layer and then application layer I have left. That is one of the core part. I could not do the core part because I have to do some introductory part in the beginning. I am ready to do the other two parts also. Okay. If you find time, please tell me. I can do that.
Okay, sir. Okay, sure, sir.
Okay. I have completed only physical layer. I have Mac layer. I have the application layer. Then I have security. Then I have the standardization. All of them are linked with the machine learning.
Excuse me, sir.
Okay.
Excuse me, sir.
Yes, ma'am. Shall I finish? Shall I close it?
Yes, sir. Thank you, sir.
Sir, It was a very nice session, sir.
Thank you.
Those who wants to do research and doing research in ML, for
Okay.
those intelligent communication, 6G necessity for ML, challenges in 6G and future ML, all these topics are very useful, and to publish good journals also.
Yes, sir.
You have given lot of research ideas, sir. Thank you very much, sir. And you shared your industrial experience also. Thank you very much, sir.
Okay. Thank you. Thank you. Shall I go off the line?
Okay. Thank you very
Sir,
much, sir.
thank you, sir.
Thank you, sir.
Great. Break ಆಗಿ ಎಷ್ಟು ಹಾಕಿದ್ರು?
I request the participants to fill the attendance and the feedback link, which is already shared in the chat box. And also you can come back for the next session at 11:30 sharp. Thank you.
ಈಗ ಮೆಸೇಜ್ తీసుకో మ్యామ్ వ్యాలిడేట్ అదే ఓటర్ థ్యాంక్స్ అయిపోయాక అది నో నో
Good morning, sir. Bharat Gupta, sir.
Good morning, sir. Bharat sir.
Good morning, ma'am.
How are you, sir?
I'm fine. How are you, ma'am?
Fine, sir. Fine. Thank you, sir, for accepting our invitation and giving talk.
No, it's my privilege that the association with you is good, and we are continuing it for long. And whenever we'll see this type of opportunity, we will try to grab it and try to share the something which I know. I'm not a encyclopedia of all the things, but whatever we know, I know that I'm trying to share it with the audience, and let's see that how they appreciate and how they take it forward for this, because the topic is very new and the things are still in the process. Yeah.
Welcome, sir. Welcome.
Thank you, ma'am. So once you are ready, just let me know.
Just now?
Yeah, ma'am. Good morning, sir. I just wanted to give a brief introduction to you. After that, you can start. Welcome back to the next session. I am pleased to introduce Dr. Bharat Gupta, our next guest speaker, who is going to talk on deep learning and its applications in wireless communications. Bharat Gupta Garu is the senior member of IEEE and having an experience of 18 years in education and research. Dr. Gupta did his graduation in 2000 and post-graduation in 2003. He did his doctorate from University of Rome, Italy in the year 2011. He received the Indian Young Research Award from the MIUR, Italy. Presently, he is working as an associate professor in the Department of Electronics and Communication Engineering, NIT Patna. Dr. Gupta is the chief investigator for the project Scheme for Financial Assistance for Setting Up of Electronics and ICT Academies at NIT Patna, sponsored by the Ministry of Electronics and Information Technology, Government of India. Dr. Gupta is the professor in charge of Incubation Center, NIT Patna, and nodal officer for Bihar Startup at NIT Patna. He has published more than 70 research papers in reputed journals and conferences. He is the reviewer of many international and national journals. His research areas covers mainly wireless body area network, routing and MAC protocol for medical wireless communication, ICT for healthcare, Internet of Things, medical IoT, FM ultra-wideband communication technology, and machine learning. Welcome you, sir. Over to you.
Thank you, ma'am, for this nice introduction. And I hope that we want to introduce as a faculty, it's better. And as a researcher and as a learner, always the lifelong. So that's a brief and sweet introduction for the faculties like us. So thank you so much. And if you allow, I can just try to share my slides. So may I share the slides?
Yes, sir.
My slides are visible?
Yes, sir.
Yeah. So I hope it is in the presentation mode, and
yes.
Everyone is able to see my slides. And my voice is clear, I hope, because of this pandemic, COVID-19, we are come to a new paradigm in which we have to speak virtually with the audience, and in present of you just a computer screen. So I don't know how, because as a teacher it's very good that if you have a people in front of you or the students and the audience in front of you, so that you can adapt or you can change yourself as per the requirement of the audience. So this is, if you see that what I have said to you right now, that the human beings, that what we are here, they can adapt as per the environments. So that is the advantage we are trying to take or inculcate in the new generation of the communications, I would say. So I will start. This today's talk of the topic is deep learning and its application in wireless communication. Just a moment, ma'am, my video is on. Just a moment, please.
It's on, sir.
So, like, with your permission, can I off, or like, is it necessary to be on?
Not required, sir. You can turn it off, sir.
Okay, thank you. So that I will have a good bandwidth.
Yes.
So, yes, I hope the slides are again visible, and I'm going back to this. So, I would be very thankful to Professor Padmasai ma'am that she has invited me and the whole organizers, and especially one of my student is also there, Shravan Ramakuri. So they have contacted me and yes, grabbed that opportunity. And this is challenges in adapting machine learning towards the 5G and 6G communication. And today's topic, which I am going to deal, is deep learning and its application in the wireless communications. And ma'am has already given my small introduction, but still myself, Dr. Bharat Gupta. I'm working in NIT Patna in the Department of Electronics and Communication Engineering. So before going to in the lecture, that today the outline of my talk that I will go in that. First, I will give you the introduction, that actually the demand of future trending applications. And second, that why the learning is required, and the introduction to the deep learning, basics of the deep learning, why deep learning algorithms, motivations for using the deep learning, expectation from 5G and B5G wireless communication, and finally the references and the conclusion we will see. So I will just tell you about some statistics before starting, because as the new applications and new paradigm is coming up, so with that the requirement of or the expectation from this communication is becoming huge. So if you see that but the Ericsson has done a survey, and he found that almost 50% of the smartphone traffic will be on the 5G network in the next 5 years. It means that the people who are using smartphone, they will because of the enormous applications, they will use it everything through the smartphone, and by that the uses per smartphone is going to be enhanced also. So right now with this it is around 10 GB per user or the per smartphone, and which is in the next five year it is going to be like 35 GB around, and on which the most of the traffic is because of the video traffic. And in terms of the statistics, if I say 60% mobile traffic is because of the video traffic, and which is going to be increased to 77% by the year 2026 or in the next 5 to 6 years. So with that, why this video traffic is increasing? Because as we know that because of the OTT platforms and the online classes due to this pandemic and all, they have increased the video traffic on these smartphones. And as the traffic increases on the smartphones, the whole load will come on the new communication networks like that. So if you see this slide will give you a little bit introduction that approximately 66% of the present population is using the mobile phone users. So why I'm telling all these things, because it is related, that because we need to know that how much load we are putting it on our existing network. So if the existing network, communication network, can cater this all needs, or can we need some improvement? So how do we do that improvement? If we are able to do this improvement, can our traditional and conventional communication system technologies or the theories are able to handle this all, or we have to think something new paradigm or the new solutions by which we can cater all this huge requirement. So with this, like 66% mobile users are there in a whole world, in which around 59 or approximately 60% users are internet users and active social media users, which is another part which adds up the load, which is around 54%. So if you see in overall that really the tremendous pressure is on our communication networks, and when we move towards this, we have to look forward for new and new solutions, and so that we have to pop up, or we have to see some interdisciplinary domains where this solutions can be come up. This is something I would say the global mobile network data traffic, which is a whole month, that is the exabyte. Initially, as you can see, this is all increasing day by day, and up to if we talk about this mobile data, as you can see, it is in this color, and it will in the next 5 years, it is going to be increased up by almost I would say the 7 times or 10 times right now what it is having. And so along with that, if we see in a overall country-wise this mobile data traffic per smartphone, as you can see in the we have find out this global average, that initially it is just 7 GB per month, but now it is in next 5 years it is going to be 25 GB, and as per the country variations, this is changing, as you can see it over here in this table. So the North America is having maximum data eating, I would say, in presently as well as in the next 5 years. So this is all slides will show you, and because why this traffic is increasing, because when we talk about the advances that what we have done in this communication technology, that will change the completely the paradigm over here, and there are, because of that, so many new applications are coming up, like augmented reality, virtual reality. We talk about ultra dense network, underground communications, underwater communication, in the medical field, in the robotics fields, IoT, smart city, self-driving. So there are a lot of new emerging applications are coming up, and because of that, it is so many challenges, new challenges are imposed to our present system, and for that we need to know what is the channel model. We need to know that how much low latency that we can provide to the large scale super dense networks and etc. So these things that which we have to see. This whole applications which have the small part of the application which I have told you, and this all going to summarize in this 3 triangular structures, which is EMBB, EMTC and URLCC. That is the enhanced mobile broadband, massive machine type communications, and ultra reliable low latency communications. So what we are expecting from enhanced mobile broadband, that even we want the connectivity is as per the fixed line, at par to the fixed line, and we want that high data rate and which can cater the high traffic volumes to this. The massive machine type communications, it means that as the IoT grows on, as the smart city grows on, smart home concepts are coming up. So very massive number of low power sensor devices are coming into the picture. So as they are coming into the picture, that we have to cater all of them together, and that comes under the massive machine type communication. And when we talk about the ultra reliability low latency, because when we talk about the medical terms or when we talk about the industrial automation and the self-driving things, so we need a ultra reliable systems. The reliability of the system must be ensured, and the latency should be very low, because otherwise this type of applications we are not able to cater with that with the proposed systems or in the 5G or beyond 5G systems. This is what I have given a small picture just to understand that what we are expecting from enhanced mobile broadband, ultra reliable low latency communications, and machine to massive machine type communications. So we have divided into this whole. So if you see, this is the smart city where everything is connected, smart transportation, smart home, smart hospitals, smart health, everything should comes under this, and in which the small sensors, they have to communicate with each other and gather and transmit it to the coordinators, and so that the intelligent decisions can be taken up and everything is at your place may be possible. So that's why this massive type communication comes to the picture, because in this we talk about the device to device, we talk about the machine to machine, we talked about the vehicle to vehicle, we talked about the smart home to smart appliances to smart appliances. So that all comes here in the massive machine type communication. Enhanced broadband, as I told you, the huge amount of data is required, high speed that is required, that is we are expecting, that is gigabyte in seconds. So if you see that the people are expecting around 10 Gbps of the 10 Gbps as a peak data, and the low latency up to the 1 milliseconds that we are expecting from it. And ultra reliable, as I mentioned, the self-driving, augmented reality, and the industry automation requires the high reliability and the low latency communication. So this is all the pictures that which I have tried to gather and show you in front of you, so that you have an idea. So that is what we are planning. This is the I will tell you some verticals and where we are expecting that 5G will enable these services, and what are the drivers that for which we are able to cater this verticals, and for that what type of enablers and what is the requirement from the networks, that is we are saying. I'm put some 1 or 2 minutes over here to see actually that what is the basic requirement that which we are dealing. The education sector, yes, we and because of this pandemic, everybody has seen and everybody has understand the need of this education sector, which is through these online platforms. So what we have to do in the education sectors, that we have to do with the remote delivery, immersive experience. So for that, what we have to do, we have to start the video streaming that we are doing right now, augmented reality and the virtual reality, so that everybody can understand that whatever it is going at a distance are near to me. And for that, the expectation from the network is the larger bandwidth and the low latency. So this is this column, if you see it over here, is the fourth requirement column, is the demand or is the expectation that which we need to do it with the existing traditional or conventional communication systems, or in cooperation with other technologies or the other techniques by which we can enhance the performance of our system and to get this requirements. Second one is the manufacturing sectors, in which we want for a industrial automations, and this is the requirement, or this is the I would say the one of the point of the industry 4.0 concepts, that every industry is going for automation, and IoT systems are implemented, every machinery and everything is going to be automated. And that's why this massive IoT networks are required. And for that, we require the high connection density. High connection density, it means like in a small area, we have to get a lot of devices, a lot of sensors, or a lot of machines to handle. Ultra reliability, yes, because a small gap in the network can create a hazard. Low power consumptions, because we have to use it for a longer durations, because we cannot change it each and every time. So this is the basic three requirements that which we are expecting from our network. And in this 5G or beyond 5G, that what we are expecting, we are saying that 10 years of the battery life that which we can give it to the network, as well as we can cater approximately 1 million devices per square kilometers. That is what the expectations we are trying to handle. Healthcare, these remote diagnosis and intervention, long-term monitoring is required in the health sectors. For that, enablers are, we want to video streaming, augmented reality, embedded device, and advanced robotics. For that also, low power, high throughput, and low latency requirement is from the network is there. And then smart grid, intelligent demand, supply control, power line communications, because nowadays we are talk about the whole electricity is on the smart grid of our systems, and for that the enablers is IoT sensors and the networks that which we are giving. And for that, the high reliability and broad coverage of the networks and low latency is required from our system. Entertainment, yes, we know the OTT platforms are coming up, and we want more and more good resolutions, good multimedia experience like 4K and 8K resolutions. We want more gaming and media industry should, they are the drivers. And for that, naturally, the video streaming and the augmented reality and virtual reality is requested. And for that, the large bandwidth and the low latency. So if you see that, if I jot down the requirement, let me just finish another two, the automotive and the autonomous cars. So for that self-driving, the major drivers like collision avoidance and the intelligent navigation and the transportation systems that we have to remove. And for that, we are seeing towards the vehicle-to-vehicle communications, vehicle to infrastructures, and other ITS, that is the intelligent transport systems are there. And for that, again, the requirement of the large bandwidth, low latency, less than 5 milliseconds. And as I previously I told you that we are trying to make it 1 milliseconds, and the high connection reliability, it's almost like 100% is not possible, but still we have to see about 99.999% of that reliability things. Then comes to the very big part, that is the smart city, that is the connected utility, transportations, health care, education, and all amenities are going to be provided in the smart city applications, and in which again the massive IoT, automations, cloud infrastructures, artificial intelligence, and again the requirement is like large bandwidth, high throughput, high connection densities, and low latencies is to be required. So if you see that everywhere we want the large bandwidth, low latency, ultra high reliability, low power consumption. So this is we are expecting from our network, and for that we need to have our physical layer should be like in an optimized way. Each blocks of the transmitter and the receiver should work at their optimality, and the resources what is available with us can be properly utilized and optimally utilized, I would say. So with the existing technologies, this new requirements and place a real challenge in front of us in that how do we achieve all these things, and the existing technologies has their own design issues and their challenges, because whatever we are doing, we are trying to modulate into the mathematical form and try to make a model with the with equivalence to the mathematical representation of that environment or the scenario. But whatever we will do, it is not as to the real scenario. So that's the always there is a gap over there. So these are the motivations that which we look. Then as I told you, this whole three things: low latency, ultra high, the high reliability, the high capacity. For that, we need an extensive research into the 5G communication and the beyond 5G over there. But the existing traditional, as I told you already, the existing conventional communication theories had put a restriction, and there is a, I would say, the performance improvement is restricted, and that leads to a severe limitations to achieve this this demand. So what we have seen along this, the deep learning is as an emerging field, and it can be recognized as a promising tool to handle the complicated communication systems and their potential for further optimizing the wireless communication. Why we are looking for deep learning? Deep learning, we have seen that it has shows a great results and the great better results, I would say, in the computer vision, natural language processings, and the image recognitions and all there. So in that, the deep learning part is they will learn by themselves from the from the environment, and accordingly it can cope up the challenges of that. This deep learning, before going to the deep learning, it is very important that what is learning, from where this deep learning comes, how we show or how we relate the human thinking to the machine thinking, or the machine can think in terms of the human brain, and slowly this learning convert into the machine learning, artificial intelligence, and then machine learning as a subset, and then it comes to the deep learning. And before that, the neural networks, which is a mimic of our human brain, and the deep learning is the basics of that neural network, or the deep neural network, DNNs. So what is this learning actually in a very short terms? Because even in the communications, we have to we will see the real-time data, and on that basis we will put it into the model, and then model can suggest that the conditions of the environment, and accordingly the system can take a decision. So learning is basically the act or experience that we will how we experience the things, and like I would say the smelling, the tasting, the touching, viewing the things, all these things. Knowledge or skill acquired by the instructions or studies, like that is what we are doing. We are trying to train the systems. Whatever we know, that we are giving the input to the system, and then system can get a knowledge. And there is a by changing the behavioral tendency, that is also the you can say the learning. So the way it is changing the things. So if I say the learning gives the knowledge and the knowledge is converted into the intelligence. So knowledge is nothing but the collection of skills, informations a person has acquired through the experience that is we have, and the ability of applying this knowledge to some task is an intelligence. Means from knowing the environment we can think intelligently, and that's why the knowledge is wonderful, but it fades as techniques and technologies come up, but intelligence sustains. Because once I learn, once I say that it is a computer, so I can see whatever the form it is there, whatever the changes it can be done in the picture, I can say that it is a computer. So that is we'll say the knowledge sustains over there, and that's the definition will come as a AI, the ability of a digital computer, a computer controlled robot to perform tasks commonly associated with the intelligent beings. So AI is basically to learn or perform tasks with the help of the machine. So if you see this is the Venn diagram. The artificial intelligence is a bigger field, and which says that any technique which enables computers to mimic human behavior. I mean, it can perform the task as the human being can do. Similarly, the machine learning, which is nothing but a subset of this artificial intelligence, is the branch, or it is a subset of artificial intelligence, which is based on the idea that system can learn from data, identify pattern, and make decision with minimum human intervention. So initially what we are saying, that with the artificial intelligence, we are saying that whatever the human can do, the same things can be performed by the machine. The machine learning techniques which help us that the human intervention can be reduced. They can learn by themselves from the data which we are giving to the machines. They can take the decisions by themselves, and in which the human part is minimized. Again, because here, if you see this machine learning, we need a data, and in the communication system, if we see, the availability of data is the main problem over here. We cannot, it's a very less data is available on which we can train our machines to take the decisions. So that's a one bottleneck over here, that we don't have data in the communication systems. Then deep learning, again, which is a subset of machine learning, which makes the computational on the multi-layer neural network feasibility. In that, we will make the machines that our human brain works. And we have designed this deep learning, or I would say the neural network models that the human brain performs. And in the next few slides, we will see that how the brain can work and how we can convert that the mechanism of understanding and relating the things and taking a decision of a human brain converted into the or it will be given to the machine. So what is machine learning? It's like automating to the automation and getting computer to be programmed themselves. The issue is that you have to write a program, and the data do the work instead. I mean, you need a data, you need a software which can help us in doing this all. So if we compare that what we are doing till now in the traditional programming and the machine learning and the deep learning and even the types of the deep learning, which we the machine learning. We'll see it later on. So in that, what we are doing, we have the data, we will decide the rules, we'll give it to the system, and the result has come up, whatever the results we are expecting. So that is what we call it as a traditional programming. But as or you can say in the AI, but in the machine learning, as I told you, that we have to reduce the human intervention in that, or we want that the machine have less intervention from the external world. So for that, what we are giving the system, the data and the results that which we are expecting, that is the results, that it means we know that this is what we are expecting, and on that basis we will design the rules. So it is just a reverse. We have the data, we know that what would be the expected outcomes, and on that basis we will write a program or the machine to learn in such a way that it can give you the rules, and after that these rules can be utilized to give the output to the unknown data. This is the process that what we are doing in this. It's a most of the people knows is because it's very hot field nowadays. Gathering data from the various source, cleaning data to the homogeneity. Yes, it is required, and then we have to train a model, then model to be tested, and finally the results that which we are looking forward. This is, I have given you one flow. If you see, this is the training set over here, which is the with the help of supervised and unsupervised, and on that basis we are trying to find out the feature extractions and then applying to the machine learning algorithm, which can convert into the grouping of the object or predictive models. And once we give the new data, it can be annotated whether it is belong to this class or to the other class. So this feature extraction, this is again a limited things, and in the communication again we have because we don't have data, we don't have features, so again there is a bottleneck to apply these things in a communication machine learning. But still the individual blocks that which we have in the whole end-to-end system that which we have applied, some research has already done in that, and they have replaced these blocks with the help of the machine learning blocks and try to improve the performance of the system. Next, this is the learning can be done in the 4 ways: the supervised way, unsupervised way, semi-supervised, and the reinforcement learning. Supervised, as I told you, we know what is the data, we know the levels, or we know so that we can make it the output. Some example like fraud detection, we know that what type of frauds are there, insurance underwriting, so we know that what is the way of who is writing which way and that way. Unsupervised is the labels or outputs are unknown. We don't know what is the output, we don't know what is the label and which class. So generally we have to do the clustering, we have to make the rules in that, like that. Semi-supervised, it means it is a mixture of these two, supervised and unsupervised. Labels or outputs are known for a subset of the data. Whatever the data is available, for a small part we know, and that way we call it as a and that mostly the people use in the medical predictions. Reinforcement learning, basically this is focus on making decisions based on the previous experience. This is what the we know the previous experience, and on that basis we will give the decisions, we'll give the rewards to the system, and that rewards may be positive or negative to the input system, and accordingly the system can change their values or their weights and then produce a output, and until unless this will give you the exact requirements. So like game artificial complex decision problems, and the reward systems are the main points. I told you that the first two have already shown you the traditional programming and the machine learning. So machine learning, if you cater this three, supervised, unsupervised, and reinforcement learning, what I said to you is earlier. So in the supervised, that we have the answers or the outputs or data that make the rules. Unsupervised, we don't know anything, so there is no known data, no label data, so only we are giving the data, and the unsupervised learning will classify the data, and that makes the rules, the feature well restricted. And the third one, or the reinforcement learning. So we have a reinforcement agent, the reinforcement environment. We will perform the action, and on that basis the rewards are given. So rewards is basically the feedback given to the agent, and the agent, based on the rewards, it can perform the action or adds or subtract the things over there, or it can adjust the parameters accordingly to make the correct decisions. So when do we use machine learning? Machine learning it's not like that. Why we are using? So I'm trying to show you some pictures. This I have taken it from one of my colleagues' presentation. I like that. That's why I'm just putting it over here. So sometimes we want to save energy. We want that we can find out some time for ourselves, and that's the reason that we can go for a machine learning. Human expertise does not exist. When we talk about that, where the expertise of the humans are not there, or the human errors are more, so we can think of applying the machine learning algorithms. So in the medical fields nowadays, it's too much applicable there. And here you can see we know that no one has the experience on the Mars, so we have made a machine learning which can help us. The human can't explain their expertise, like speech recognition. We cannot say that who is who and what is the language and what words, so we can apply it over here. Models can be customized as personal medicines. So as I've already given you that the personalized medicines means that if you have this features, so on that basis what type of medicines can be prescribed to you, that can help, not completely reduce, but it can help to the doctors. Or when we have a huge amount of data and where we cannot handle by a human being, so naturally we need a machine learning models which can help us to do all these things. So these are some ways where we can do, and a classical example of this, like this is the numbers, and it is really very hard to what makes it to in that 2, 3, 4 and like that. So this is the classical machine learning problems, and most of the people who are working in this machine learning, they have gone through with that. The point is that if you see that this is the machine learning, so till now what we are doing, we are making this data available, and on that basis we are giving this input to the machine, and the machine take the decisions. But here again the human intervention and the label data is requirement, and all that. The biological inspiration comes over here. We know that humans perform very complex tasks like vision, motor control, language understanding very well. So these things can be done by human beings. So, but how they do all these things? So one way to build intelligent machine is to try to imitate the human brain. This is one way that which we have done it. But to perform it by its own, how they do learn, how do they without a data, or how do they the humans can relate the things. So this is really a very complex things, and that we will implement into the next sections. Just to say you some things about the human brain, I would say the brain is highly complex, non-linear, and the parallel computers, and approximately 10 to the power 11 neurons that are densely connected, and per neuron is around 10,000 connections are have, and so that the this is what we have understand till now about the brain. And neurons are much slower, that is almost a millisecond they will take, but our the semiconductor devices or the gates that can walk very faster. So if we mimic the behavior of human brain into the machine, so you can see that how fast we can perform and the things. The complex perpetual decisions are arrived at quickly. So with this, we can do it in very complex decision in a moment. And the felicity is that the some of the neurons structures are present in the brain, but through the learning they are always developing and they are trying to adapt the environment over there. If you see, this is just a pictorial view of a biological neuron, which is and with this biological neuron you have tried to mimic the models and see that how they are working. So up to what we understood is like this much is from the human brain. This is the, if I say this is the these are the dendrites, which is the input given to this cell, and this is the cell is the center which support the light, and these are the axons which are used to transmit the cell information or the message to the other neurons, and this is the output of that neurons, and this is the electrical impulse signals that which we are giving. And once this the output is above the threshold, it can be shared to the next neuron. So this some few terms which is maybe important or not important, but the synapse, I will show it in the next slide. Yes, this is. So this is the small gaps which I'm showing it over here is the synapse, and this is the nerve impulse which is going, and it is once it is above the threshold value, it can be transferred to the next neurons, and that way it is communicate and it is pass the information to the, and on that basis we are able to take the decisions, and this is what we do. This is just a pictorial view of this how this electron they are passing through one neuron to the another neuron. So based on that, we have developed this artificial neural networks, and which is just a mimic of our human brain. Again, massive parallel distributed systems, synaptic connections, strength among neurons are used to store acquired knowledge. The knowledge is acquired by the network from its environment and through the learning process that which we are getting it from. This is the properties, the learning from the labeled and unlabeled ones. We have to adapt the changes. What is, I mean, it should be adaptive in nature. That's why we are giving the feedback, and non-linearity, that it can work as a non-linear active functions, because we cannot divide the whole complex systems into the two parts, bilinear parts. So there is a non-linearity, active functions are essential. It should be the fault tolerance, the system. It means that the system should able to work even though there is some networks are not in function, or the neurons are damaged or like that. So even though our brain is working after so many diseases and all the things. Then this is the might be a better alternative than the classical solution for the problem to be characterized, that it should be a high dimensionality, noisy, imprecision and imperfection data can be handled by this. A lack of clearly stated mathematical solutions or algorithms are available. So what we do, this is actually the exact thing that which we are moving ahead in the artificial neural network or the deep neural networks. Because as I told you that we cannot mimic everything, or we cannot convert every real scenario into the mathematical solutions. So that's the limitation what we are facing. So only the data, the available data can make a model which can replicate the real instances over there, and the whatever the imperfectness in the data, noisy in the data, or whatever the dimensionality of that, because as we have seen 10 to the power 7, 11 neurons that which we are giving, and around 10 to the power 4 inputs that which we are giving. So like a lot of dimensionality can be handled with that. This. So this is the I would say the artificial neural network, which is especially shown inspired by the biological neural network that constitute by the animal brain, which I have described a little bit earlier, and we're trying to convert into a model. So as I am just fully making it like this is the way the axioms from the another neurons, which is axon, we are giving the weightage synapse, like there is a gap, and then it will the synapse is there, then the cell body where we have to sum up all the inputs with there, and then we have to pass it through an activation function, and once the output of this activation function is above the threshold, then it will pass on this information to the another neurons, otherwise it can retain it with us. So whenever there is a change in the threshold, the change in, so here that you have to see that what is the threshold, what is the, how the we can what type of activation functions that which we can incorporate over. Generally we are using the unit step sigmoid functions and the ReLU functions as a activation functions over here, and this is all non-linear functions that which we have to consider over here. So this is what I have already told you over here. So the basic neural network is node or units that which we have to consider, the weights that which we have to assign for their importance, and the node applies to a function that is a weighted sum of input. Then all weights are the weights W are learnable and control the strength of influence in its direction. So positive weight we have to give, or the negative weight we have to give to one neuron to another, depends on that the requirements. So this basic model dendrites carry the signals to the cell bodies, and they are summed up, and final sum is to a certain threshold value, and neurons can fire only when there is a spike which is more than the threshold value. So this is the architecture that which we have to use it for our networks. So there are the three layers which we are talking. This is the input layer, hidden layer, and the output layer that which we are talking about. Input layer, no computation that which we are doing at this layer. Only the we are giving the input to this from this layer. Hidden layer, where this all computation intermediate processing that which we are doing it over here, and they will take the sum up of all the inputs which are coming from the nodes, and on that basis we will pass it through the activation function, and then finally we map it to the desired outputs. Here it's fine. I have already, yes. One thing which is non-linear activation function, that such networks to compute non-trivial problems using only a small number of nodes. If the artificial neural network, this is a functions called the transfer functions, and this function is called the transfer function, which compute over all non-trivial problems. It's not necessary that the small problem which can be solved, it can be handled. So this is what The learning rules, I'm just showing it to here, this here. So what I have explained, this is the input layers in which this all inputs are connected to the hidden layers where they are going to summarize, sum up the things and pass it through the activation functions, and if these are above the thresholds, and it will produce an output, and if the output is as per our requirement, it's fine. Otherwise, we'll give it. We can modify the weights and the threshold values of the system. From that, we have this perceptron. We have tried to make the perceptron, which is a single layer neural networks or the multi-layer perceptrons of the neural networks. And perceptrons initially with a linear classifier, which is based on the supervised learning, and in which we have 4 input parts, consist parts like input values, weights, bias, net sums, and the activation. You can see it over here. So like this is the constant, this is the bias that which we are giving, this is the inputs that which we are giving, this is the weights, and finally the weighted sum over here, and then everything is passed to the step we are getting. So this is yes, go ahead. So all the inputs, this is the part which I have mentioned it over here is x are multiplied with weightage, and all the multiplied values add ups, and there is a weighted sum, and then we have to apply correct activation functions. This is like over here, and sometimes the unit step functions, or the sigmoid functions, or the ReLU functions, or it is here that we have to see that what type of threshold functions or the activation functions that which we have to use it over here. So now, after learning all these things and mimic these all neuron structure into the model with the help of neural networks, and which is the basic unit of our deep learning. So deep learning, as I told you, is a class of machine learning algorithm using the multiple layer to progressive extract higher features from the raw inputs. So it will helpful. So if you have a more number of features, you have to put more number of the hidden layers over there, so that it can produce, or it can give you the exact output. And this was introduced in 1986 by Rina lecture, and the deep learning by her. So now we'll see that what is deep learning. Learning is about automation. That it means that which we have to make the things to be automated, which can be performed by themselves, which can be features can be extracted, the decisions can be taken up by the machine. So if we see the steps toward enabling the computer to learn without being explicitly programmed and visualize the world as human do. So we are trying to make the machines they can learn or visualize from the they can make the program by themselves by learning the environment as the humans do. And deep learning is based on the neural network architectures, which is nothing but a mimic or convert the representation as a human brain. Then the deep learning type of learning model learn to perform classifications tasks from images, text, or sound. So they will do the learning tasks by themselves with the help of images, text, or the sound that which they are getting it from the environment. So what exactly the deep learning? As I told you that the neural network, simple neural network, or the deep neural networks, it is nothing. It is the deep learning is nothing but a deep neural network that in which the multiple hidden layers are there, and the deep is referring that how many depth of the layers in the neural network is there. And this, with the help of this hidden layers, we can generate the expected outputs that which can perform our systems to be more matured. So if you see that what's the difference between this traditional and the machine learning, so in that if you see that we have extracted the features, and input is given, feature extraction, based on that classification we have applied, and they will take the decision. But in the deep learning, this is done by itself, that convolutional neural networks, the learned feature, the features are learned by themselves, end-to-end learning is there. And these features this is the concept, and this is the thing which is required from a technique by which we can implement in our communication system, that the features can be learned by themselves. It's a complete end-to-end learning must be there. It's not only individual block level learning is there, so that we can optimize the global optimizations of the systems can be achieved. And this deep learning, in this picture, performs end-to-end learning by learning features, representation, and tasks directly from image, text, and sound. So this is the input that which we are giving to this, and end-to-end learning can be performed based on the features, representations, and the tasks we perform over there. So this is the a sort of example, and then we come down to the main part, that what are the possible applications that which we can look in the communication system and can be applied. So here you can see that different the picture or the text, they are in a different orientation, but it's still because of this learning, so many parameters are extracted and can be recognized over here. So this is what we understand, that till now what we see here is that what is actually this merits of the applications or the data which is coming, and which we have to cater on the existing conventional traditional communication systems, and which is not able to cater this all huge requirements. So for that we have to improve the performance, but the traditional systems are putting restrictions. They don't have the I would say they don't have the proper models which can improve the performance of the systems. So here we will see that what is directly we come to that the beyond 5G, that what is the expectation. So as you can see, the 5G is still not matured, and the 4G LTE systems or advanced LTE system are still improved version, and we are moving toward the 5G, and some of the countries have already deployed, but the people are very demanding, and we have seen that the in the futuristic future applications are more demanding. So that's why we are seeing that what is the 5G can be expected, that the capacity should be increased, that is the 150 terabytes per second. So user experience, that is up to the 10 Gbps, latency as low as 1 milliseconds, 10 million of devices per square kilometer. Location accuracy can be in terms of the centimeter or the millimeters, and the energy efficiency must be there, so that the battery life can be increased. So we need we have to connecting the intelligence of all the available sensors. We have to program, we have to integrate all the sensing, we have to make the system to be sustainable, we have to make the system to be trustworthiness, affordable, and it can be scalable, so that the need of the can be taken care. So for that, like this gives us the motivation. This gives us the point where and we can apply. So in that we have taken it from Georgie Wiley, Imperial College of London. He has given in the presentation that basically the challenges in the current systems. I've already told you previously also that the mathematical models versus the practical imperfections. So we cannot represent each things with in the mathematical model. If it is done, then yes, our conventional models are good enough to gather all the things. So there is a really gap between the mathematical models and the real or I would say the practical scenarios representations. So conventional communication systems rely on the mathematical express models for each block. So in the, if you see, not here, I will see it later on in the part when we come to the end-to-end system. So the conventional communication system, basically they are based on this mathematical models for each blocks. But when we talk about the real world and with this phenomenally new I would say the new applications, and where they are so much demanding and the systems are complex, so it is really difficult to express this mathematically, the new systems. So we need, this is really the challenge we are facing, and that restricts the improvement in the performance of the existing systems. Then second, block structures versus global optimally. So if you see that till now the optimizations of the communication systems is done at the block levels, like we have optimized the channel estimations, we have done MIMO systems, we have optimized the coding, encoding, encoder or decoder, we have optimized, but these are individual, but that will not guarantee that the whole system will give you the optimal solution. So that's really a challenge. By giving the optimization to one or two blocks, or will it depict the overall or the global optimally? No. So this is the problems, like I would say that traditional communication systems, so many blocks like channel encoding, modulation, signal detections, which are designed and optimized within locally. But global optimality cannot be guaranteed by this block level optimization. So as a result, we need a system which can work globally or end-to-end optimally. Now, I think you can relate the previous slides in which I mentioned specifically the neural networks, artificial neural networks, or the deep neural networks, which can reduce the importance, or which can reduce the utilization of mathematical model and single block optimization in that level. So that can be exploited over here, the deep learning techniques. Complexity and performance of the optimizations, yes, because systems are becoming very complex and they can perform optimally only when we can learn the environment perfectly or as equal to the real scenarios. Sequential decisions in the resource allocation. Resource allocation is again one of the major bottleneck of the enhancement performance of the communication system. So if you see in the traditional system, the resources that what we are looking towards is only in terms of the either the bandwidth as a resource or the power as a resource. So in that there is a trade-off is always like, can we give more power for the more bandwidth? Can we, if the bandwidth is less, we have to talk about the less power. How to optimize the use of the power, how to optimize the use of the bandwidth. That's why the new type of new technologies are coming up into the picture. But still this is not properly catered. So but now the new type of resources are also come into the pictures over there that we'll talk about later. So this is the challenges with the current communication systems that which we are facing, which can be or which may be overcome by our deep learning algorithms or the deep learning part. That is deep learning, as I told you, no need of models for the data-driven methods. So we don't need mathematical models. This is all done by the data-driven methods, and even the importance of the data is also because data is required. So even we have find out a GAN models which can generate the data by themselves. So the availability of data is not also a problem. Then end-to-end loss optimization of the global optimality, yes, we can achieve with that this, and may reduce the complexity and improve performance of the physical layer processing and resource allocation. Yes, this may reduce the complexity. We don't know, but there is a chance. When we have seen this deep learning algorithms, they have shown a tremendous good results in the allied fields for computer science and other fields. So we are expecting that they may reduce, they can be outperform over here in the physical layer processing and the resource allocation problems, and which can be utilized without data-driven models. Hello, am I audible?
Yes, sir, you are audible, sir.
Okay, thank you. So yes, so now we will see that what is basically the fundamental difference between the wireless transmission and the deep learning. So these two I have already mentioned about. The one is the mathematical model and the key challenges. So these are the things where we can differentiate between the traditional wireless transmission and the deep learning models, and that can be incorporated. So for the wireless transmission, yes, we need a very accurate mathematical model to enhance the performance of the system, but does not rely deep learning in that there is no rely on the mathematical model. Design approach, we have to each modules can be first represented in terms of the mathematical model, then the data can be given and then optimized. But in that, the training of the parameters from the deep neural network as a whole. So we can do it as a whole. Optimized training can be done. Interpretations, this is very intuitive because we know that what is what, but it is non-intuitive. So any decisions can be, interpretation can be done from this, but which can be improved in that way. So intuitive, we should know that what is what before giving the interpretation. Generalization ability, widely applicable. Yes, wireless transmission everywhere. This is application specific, means we can use the different models for the different applications, because in that we don't require any mathematical model. We don't have to start it from scratch. We just put a deep learning model over there, and which can learn and adapt and optimize it as to the application specific. And in this wireless transmission, we have to use a same model which can be applicable to all. Key challenges, what? Unrealistic assumptions. Yes, lot of assumptions that which you have to do, the basic, very basic assumptions that whatever we are doing in this, we have to consider that the channel is static initially. So non-stationary channels. So we cannot consider the non-stationary channel, and we cannot find out. So this is the unrealistic assumptions that we are assuming that for this moment of time we consider that the channel is stationary, and this is the assumptions that this is the AWGN noise is there, the estimations is like that. So this is the unrealistic assumptions that which we have to see, and then we have to see the performance, and on that basis we have to take the decision, intuitively decisions. And but in this too many parameters can be taken, and on that basis this can be managed. because too many parameters, because it can take text, it can take images, it can take sound, and train ourselves. So lot of parameters can be handled, which is the key challenge over there. Now, if I say this, how we implement this deep learning, this is what we have seen. The deep neural network basis. This is a single neural elements. So research on neural networks started from a single neural networks, in which the inputs are given as a their weightage output layer performs the sum of the weighted functions, and then the activation functions, and shift to the neurons like that. So this is the single neuron elements can be taken up, and the multi-layered, in which the forward neural networks, that is FNN, or the recurrent neural networks RNN, can be considered. So if you see this FNN, each neuron is connected to the adjacent layer. Each neuron is connected to the adjacent layer, but they are not connecting ourselves. And then this layers, the fully connected with the feed-forward neural networks, and that gives you the significantly reduced number of parameters to be trained, because they are all fully connected. So we require a less number of parameters that is to be trained. And the neural networks, they are determined based on the current input as well as the previous hidden state inputs also. And so that way we can say the FNN has a RNN has a memory, and FNN has a not memory. And RNN is dependent on time long run terms, and non-stationary errors can show up during the training. And here you can see that non-stationary part can be also handled with the recurrent neural network systems. The main problem that what we are facing in this communication system is the data, the real data sets, that which is not available with in the communication systems, and because the conditions are changes, the environments are changes, so volatile environment is there. So we cannot say that okay, this is the data set that which we can train our system and we can make it. So for that we can use the GAN, that is the generative adversarial net, and another one is the conditional GAN, that is this. So this, to train this deep neural network, we need really a labeled huge amount of the labeled data, and which is a real problem to the communication system. So for that we have used this GAN, and GAN is consists, as you can see in this picture, there are the two things. One is the generator and another is the discriminator. This discriminator is basically help us to discriminate between the real data and the fake data. And G, the generator, which try to plausible data, to fool D that it is a real data. So we are trying to playing the games between the G and D, discriminator and the generator. It's a two-player game. And what is we are doing? We are generating the fake data, which is some sort of real data which is also coming, and this generator will fool the discriminator by making this error to be saying that this is the real data. So this is the concept of a GAN, by which we are generating, and this will say, I would say this discriminator later on it will say that this real data and the fake data, they are almost similar, or they will consider to be the same data. So it means like that generated data is trained in such a way that it can generate the data which is as equivalent to the real data, and this is with the help of the GAN. And everybody in the most of the end-to-end communication systems that which we are using this GAN as a part. And there is a conditional GAN, which is nothing but the extension of the GAN, in which the conditional informations are to be given at both the places, as well as the generator as well as the fake data, and this the condition is same for all, so that it can correlate, or it can if you have some input, you can give the input to that. That is the conditionals of that. So this is the GAN structure over here. And some GAN mobile generated data, again it is the real data, this is the discriminator, this is the generator, and this is the classifier that which we are giving. And on that basis there is a real and fake data that they will take the decision, and on that basis they can generate this data. This is what we are talking. If you see till now in the traditional communication system, which is the block structured, model driven are there, and the deep learning structures, that is the data driven, and this is also the end-to-end. But the overlapping of these two will give you the intelligent communication system, the structure over there. So if you see the conventional blocks based communication structure, or the DL based communication utilize the power of DL to facilitate. So in that we have also utilized the block model driven. There also we can apply the deep learning. Over here model driven, and here data driven also for the end-to-end systems, that which we can apply it over here. Here if you see, the DNN can be regarded, one moment, yes. So the deep neural network can be regarded as a black box and used in each processing block individually to replace the existing algorithm, which is the overlap of the block structure and data driven module. This is the black box, which is which can be utilized and which can be replaced the block structure and the data driven, and for that to be DNN, deep neural networks. Moreover, it can be used to optimize the whole transmitter and the whole receiver when the DNN merge all processing blocks in the communication system, and such a structure is called the end-to-end communication system. So when this deep neural network merge all the blocks together, and then only we can say it is an end-to-end system over there. And here the proposal for this deep learning based end-to-end system is based on the reinforcement learning, or by the conditional GAN based end-to-end communication system that they have proposed. So if you see it in the, I'm just coming back, like if you see, this is the transmitter side, this is the, sorry, this is the transmitter side, like source coding, channel coding, modulations, and then that channel. And here at the receiver side, we have a channel estimation, channel equalization, demodulation, channel decoding, and source coding. Finally, this whole block, all block is going to be replaced by this deep neural network communication system relying on a single block. So if you see, we're done with the help of two things, which is the end-to-end the reinforcement learning, and another one is the conditional GAN. So if you see the reinforcement learning, so we have make a agent that is a transmitter. So the whole blocks of a transmitter, like encoder and the antenna systems and all, they come onto the transmitter side over there. Source data is there, then the transmitter deep learning model over there. Then we have transmitted signal, we have perform, and this whole environment considered to be the channel and a receiver together for this. So channel receive the signal, and then the receiver is giving, and on the based of this receives output, it will give you the reward to this agent. So end-to-end loss, that is optimization, what I told in the deep learning. So this is the reward that which we are giving to this agent, and on that basis the model is to be trained, and finally we can train our end-to-end whole communication system to be optimized by this. This is the one way, and the other way is The other way is that I would say this is the GAN. The transmitter is over there. Here, the channel, what we are doing. So real channel that I have told you, if you see the real data, here the generator is applied, the discriminator is applied. So the channel is giving here and there both the input to the discriminator, and the discriminator will help us in generator to say that this is as equivalent to the real data. And after that, we don't need this channel to be estimated and to know the information of the channel. Only these informations can be generated and make a model, and finally we can get this receiver side of the report. So this is the end-to-end communication based on the deep learning models, either based on the reinforcement learning or with the help of the GAN-based end-to-end communication system. The second point of the wireless allocation, as I told you that we have a lot of resources considered to be bandwidth and the power and coding scheme, optimization of the allocate limited communication resources. So basically the main approach in the traditional system, we are making a mathematical models for this and then optimize the things. But here we can do it with the help of the deep learning models, and that will help you to do that. So if you see the wireless allocation, we can first formulate into the optimized problem, mathematical model, and the traditionally solution to find out. Another way, like if we have a mathematical problem, we can use the deep learning assisted model to solve that problem. So we can apply it over here. Or simple way that directly we can use a deep reinforcement learning based approaches, which can give you the better the optimized resource wireless resource allocation to the system. Here, how much time is left, ma'am?
Sir, 1 o'clock, say 6 minutes, 5 minutes.
How much?
5 minutes.
Okay, sir, no problem.
Okay. Okay. So just let me know because I think still some material is left, but as per yours, I can stop myself at 1 and then maybe I will try to do it very fast over here. So,
okay, sir, you can take 5 more minutes also, no problem. We can start next session after extending 5 more minutes, no problem, sir. Lunchtime only.
Okay,
So I request all the participants be patient. Okay, thank you, sir. You can continue, sir.
Thank you, ma'am. So I have just tried to figure out this problem related to the 5G communication specifically, if I say, or to be the wireless communication. So if you see this, we have categorized this into the layer wise, like physical layer problems, some which can be catered, the problems which can be. I'm here giving you the research areas that where we can apply this deep learning and try to optimize our systems over here. So if you see that the physical layer, at the physical layer, these are the areas where we can apply the deep learning as individual modules. Like we can go for a CS estimation, coding, decoding scheme, beamforming, fault detection, device location, self-interference, RF characterizations, multi-user. And second one is the, I would say the network layer where the traffic predictions can be done, anomaly detections can be done. The applications layers where the different type of models can be trained for different applications which I mentioned, and then a part of the resource allocation in which we can use the models for the spectrum allocations. We can use it for the cache management. We can use it for the handover predictions over there. So one by one, I'm dealing with some of them. So if you see the first is the channel state at the physical level. So we all know as a communication student, the CSI is how estimation, how it is important, how much it is important to allocate the informations. Like if we know the channel information perfectly, and then we can use the modulation scheme, we can use the coding schemes, we can see that how much the channel is stable, then more data rate we can transmit. So these informations that if we know that what is the channel state informations, and this can be as a considered to be the stationary, but in a non-stationary way if we are able to find out. So that requires that way help us to optimize the resources. So, but what we have seen, the traditional what we have seen, like this will give you the high computational capabilities required, different types of the technologies that which we are using in the 5G, like MIMO, millimeter wave, OFDM, other things that which we are using. So that becomes more complicated to make a realistic model, mathematical model, which can consider all the technologies together and give the channel estimation. So for that, what we don't have to know these models, that what type of technologies that which we are incorporated in the communication system. So only based on the informations of the channel with the help of the GAN model, if we can train, if we can generate that data, and on that basis if we can take the decision, that will be very helpful. So this is the one area where we can apply the deep learning. Here I have given a depict that based on the CSI feedback, the deep learning models can be had. So if you see the downlink, like over here, the transmitter from this base station to the user that we are giving, and the CSI, because of this encoder that the channel state information is giving over here, and as well as we are giving it to the transmitter. So then only we know about what is the CSI information. But if we know with the help of deep learning models, so the encoder and decoder, if we apply this deep learning models over here, and then can take a decision while transmitting this data from base station to the user, it will be optimized. It can be done. So this is the way where we can apply the deep learning. Coding and decoding scheme representations, as I'm just showing it over here, like if you can see the transmitter, the channel and the receiver. So we have to encoder network is to be there, which is the complete mini 4 or 5 or 6 hidden layers must be there, and then the encoder network is there, and finally we can make a decoder network which is as equivalent to the receiver side, and which is taking care of the what is the channel is there. So this is the thing that generation of information at the source and the reconstruction of such information at the receiver makes up coding and decoding process respectively, that we all know. And 5G may that we are using different technologies, so we have to know that what type of coding, what type of decoding schemes has to be applied so that it can work properly with NOMA, with MIMO, or with other existing technologies, so that the impact on the data transmissions can be reduced. The signal diffraction, fading, path loss, and scattering point can be considered over there. So this is this. We can make the encoding and decoding networks with the help of this deep learning. It can be very helpful over there. Fault detection, yes, as we know that we have talked about the URLCC, that is the ultra reliable low latency communication systems, and in which if we know what is the fault is there, then probably we can guarantee the reliability of this thing, and that depends on the how we able to find out this fault detection, because there is a heterogeneity of the 5G networks, the devices that which we are using it over here, the networks that which we are seamlessly connecting in the 5G networks, they are very heterogeneous. So detecting this fault is and where it is happening, it's really a big task. So there also we can apply some fault detection, deep learning techniques in understanding the where and how this faults are occurring, and on that basis we can take the decisions over there. Device location predictions, yes, it is very important to know the handover sessions, quality of the service, resource management and all. And if we can understand if we can predict what would be the next step and what would be the possible direction that user is moving, or what is the exact location of the mobile user is there. So this will be helpful in making the directional memos, so that we can provide the high data rate, we can save the energy while providing the I would say the very directional transmitters can be utilized over here. So this is one. Another one is the anomaly detection, and because as I told you, there is a heterogeneity in the all networks, so we don't know what type of malicious identity come into the network. So we should know that what is the fault tolerance or what is the anomaly is taken care of in the 5G system. Traffic predictions, yes, we don't know what is the, because it can be utilized in the smart cities and the smart systems. So we know that the internet traffic is also increasing by too much in next 10 years down the line. So if we know that what is the traffic prediction, so on that if we can take the decisions and we can apply our resources in that proper way. Predictions, because it is very important. If we know the when we have to do this the handover of one network, one base station to the another base station, or one network to the another base station based on this RS reference signal receipt power or the reference signal receipt quality power. So if we know that what is this going to be the next step of our user, so on that basis this handover predictions can be done, and where the seamless connectivity with different speeds can be done to the in the 5G networks. This is the cache optimization. This is basically the resource allocation part is there, in which the multimedia traffic is going to be dominant. So, and if we have to give it everything on the channels again and again, it is a problematic. So what is if we can keep this cache optimization at the edges of the network, so it will be a very fast, and as well as it can be every time can be fetched. So best location for storing this data is to be taken care by this deep learning models, and we can find out the optimized or the best location where we have to store our multimedia contents over there for that. So because they know that what is the trend, that how the people, which what type of data or what type of material, what type of content that the user is looking for that, and on that basis we can keep if that content in nearby area. So that way models can help us to keep the cache optimization. Resource allocations, as I've already told you, that will helpful to dynamic and complex network environments. And yes, application characterization. Yes, cellular networks, they are self-organization networks which can plan, deploy, operate, and optimally mobile resources in a simple, fast, and automated way. So this type of applications that which we can make the quality of the network better, and as well as it can increase the revenue of the systems. One last slide, I'm just showing to you. I've done it a little bit faster the last some pages. This is the network, a summarized way where this deep learning applications in the wireless networks can be used and optimize that block, individual block, not as a whole end-to-end system, but yes, end-to-end also we can do. So this is the physical layer, data link layer, network layer, upper layers, network security layers. So these things we have, some parts we have discussed, but still it's a very wide topic and lot of issues are there. And so this is the chart which can help you to understand and think, and you can choose as per your comfortability and expertise the topic. Now the conclusion, I would say rather why I've just say one sentence, because deep learning have a great potential to address most of the conventional communication system problem in a more flexible and mature way. This is why I'm saying, because with the heterogeneity of the network, with the phenomenal myriads of the applications, different applications, we need the conventional systems, communication system have to be improved, and the deep learning have really a great option or potential to at least address, not at a end-to-end way, but at least at a small block level can be optimized. But we have to always see further in a futuristic way, so that we can handle it in a end-to-end system way, so that the whole system can be optimized. So this is the references mostly which I have taken material from the papers which I mentioned here. This is some important references, and you can find this material over here, and you can if you miss something, if you are not able to understand something, you can always go through the references over here, and we can always discuss it further. So thank you so much. Thank you the audience, and thank you so much the organizers have given me the opportunity which we are facing in this communication system. And I hope the people have at least some understanding and some knowledge that how can we utilize this deep learning models in the communication systems. So thank you so much. I'm done from my side, and now it's open to you, ma'am. Sorry, I have a little bit extended my lecture, and I know that the lunch time is there.
Okay, sir. Wonderful session, starting from neural networks to AI, machine learning, deep learning, communications, wireless. Everything you have covered, sir. Okay, very well organized. Really, I appreciate your, even though I know how much busy you are, you have spent your valuable time for us. Thank you very much, sir.
Thank you. Thank you. So if we have some questions, you can just pass it on to me, and I will be happy to answer, because now I can understand the next session is going to be held, and so depending on that.
Sir?
Yes. So
are you there?
Yeah. Thank you very much, sir, for accepting wonderful session. It was a very nice session, sir, and you have given very useful information on deep learning and in wireless communication, from introduction to application like education, smart cities, and smart grids, etc. And what are the machine learning workflow, and when do we use machine learning and our other applications also? And mainly we focus on like 6G goals and our challenges in the current communication system. Thank you for session, sir. Thank you. It's a wonderful session.
Yeah. Thank you so much. Thank you so much.
Thank you, sir.
Thank you. So if you allow, I can just lead the meeting.
Yes, sir. Yes.
Yeah. Yes, sir.
Yes,
Okay.
sir.
Thank you so much.
Thank you, sir.
o'clock.
Definitely morning.
Definitely. So,
All of you, please join at 2 p.m. Okay, you can leave now. Thank you.
Hello, Nitin Ravi, sir.
Hi, good afternoon, sir.
Yeah, good afternoon, sir. We will start at 2 o'clock, sir, exactly.
Okay, fine.
Good afternoon all. Welcome back to the session. I take immense pleasure in introducing the guest speaker for both the sessions in the afternoon, Mr. Nitin Ravi Garu. He is going to provide a hands-on session on NetSIM for wireless communications. Nitin Garu is presently working as an application engineer at TEDCOS LLP, Bangalore, the developers of NetSIM. He has around 3 years of experience in the fields of computer networks and wireless communication. He got graduated in electrical engineering from NSS College of Engineering, Kerala. While in college, he was an active member of the IEEE student branch and has coordinated many programs under IEEE. His areas of expertise include 5G, vehicular ad hoc networks, and Internet of Things. He has worked on several development projects in these domains in NetSIM. We welcome you, sir. I request you to take over the session.
Thank you, ma'am. Good afternoon, all. So, my name is Nitin, and first of all, I would like to thank Vienna VJIT and the coordinators of this ATAL FDP program for giving me an opportunity. So, yeah, the session is basically hands-on session using NetSim, which is a network simulator tool. So first of all, I would like to show you around NetSim software. So like many of you may not be familiar with NetSim, like what NetSim is used for, what is it capable of, etc. So first, we'll have a walkthrough through the software, and then we'll be going through the 5G module in NetSim and some experiments and other features of 5G. So I hope this session will be useful, and yeah, we can start off. So I have prepared a rough agenda for the same. So like I said, initially we'll be going through an introductory part about NetSim. Like what are the different versions of NetSim, what all technologies are present in NetSim, etc. Then we have a session where we will be going through the user interface of NetSim. So unlike other network simulator tools, NetSim is a unique one, which is very easy to use. So you can easily create scenarios and analyze the performance of networks using NetSim. So we'll go through the user interface and some of the features present in NetSim. And after that, we'll be having a deep walkthrough through the 5G module in NetSim, and using which you can understand more about 5G. So like what and all devices are present in the 5G network, how the data transmission takes place in 5G, etc. And after that, after going through the basics of 5G, we'll be going through some of the examples, like what happens as a user equipment or a mobile moves away from the base station. So as the distance increases, what happens to the output or the throughput obtained? Then what happens when multiple antennas are present? Then how can we understand the phi layer, and how can we understand the overall throughput obtained, the process behind the obtaining throughput, etc. So if time allows, we'll be going through more features. Otherwise, we'll be focusing on till the understanding path loss model part and handover. So we'll start off now. So initially talking about NetSim, first of all, I would like to share a few things about NetSim. So when we started the software, so NetSim was founded in 2005, and yeah, it's almost 15 years now, and we are having 400 plus customers all over the world. So almost all the universities across 25 countries are using NetSim for their academic use and also for the research purpose. So the main unique feature is that we are the developers of NetSim and we provide the support for NetSim. So there are no third party present in between the NetSim software and the customer. So directly the people who are using NetSim will be interacting with us, the developers of NetSim. So we started with the version 1 and version 2 back in 2005, and now we have reached till version 13.0. So we have developed many technologies in our way through this software. So right now we are dealing with the leading technology like 5G and other protocols which used for Wi-Fi, etc. Now, many of you might be thinking, what is NetSim? So, like, this will be a new term to all of you. I guess some of you are already a customer of NetSim. So, NetSim is basically an end-to-end full stack packet level simulator. So, using which you can create a network, analyze the performance of network. So, unlike MATLAB and other tools, NetSim is not a link level simulator. This is a packet level simulator. So, everything in NetSim is in the form of packets. So, from one end device to another end device, the packets will be transmitted and the overall performance can be analyzed using NetSim. So, we have got many protocol libraries like the WLAN, where we have the IEEE 802.11 standard, and we have standards like A, B, G, N, and AC, which has 2.4 and 5 gigahertz frequency bands. And then for the wireless sensor networks, we have the 802.15.4 protocol library. And for the cognitive radio, we have 802.22 IEEE standard protocol. And then now we have the infrastructureless networks like the mobile ad hoc networks, where we can have multiple hops for the communication. And then for the vehicular communication, we have the VANET module and yeah, many more. And now we have the leading technology, so on which many research is going on, like the LTE and 5G modules, and also some for the defense and military purposes, we have the TDMA and military radio networks, and also the satellite communication networks in NetSim, where you can model a network and easily create and analyze the scenarios. So, like I said, what makes NetSim unique from other network simulators is the graphical user interface itself. So, if you are comparing with a network simulator like NS3 or NS2, there you have to write a TCL TK script, and which is a hectic process. So you have to write many lines of code to create a scenario and to perform the simulation, etc. So in NetSim, it's easy. You can just drag and drop the devices onto a grid environment and easily create a network. So NetSim will automatically take care of the scripting purpose in the background. So to analyze the result or the network performance, we have certain windows also present here, like the animator, which shows visually the packet flow from one end device to another. And then we have certain log files and CSV files, which gives the overall performance of the network. And then we have the result metrics, where the overall result obtained after the simulation will be tabulated and displayed. And also it's easy to interface with other softwares like the MATLAB, Sumo, Wireshark, etc. And the source code of NetSim is written in C code, and people who know the basics of C can develop their own algorithm and protocols easily using NetSim. So we'll be also providing the source code with the standard and professional versions, which we'll come to know in the coming session. And also using NetSim, you can analyze the live applications also. We have a network emulator module which allows the user to link NetSim to live applications across real devices. So that means like there will be a live traffic flow between two or more devices, and which will be interfaced with NetSim. Now, like I said, we have different versions of NetSim. For different purposes, we have different flavors of NetSim. So it's basically divided into three. One is the NetSim Academic. Then we have the NetSim Standard, and then we have the NetSim professional version. So academic version of NetSim is basically used for lab experimentation, and where we have 45 plus lab experiments present in the tool itself. So this will be basically used in universities for the lab, academic lab purposes. Coming to the standard version, uh, this is a version which is typically used for the research and development purposes. So the researchers who want to pursue their future in the networking domain can create, analyze, and write up their thesis or anything using the NetSim standard version. So we'll be providing the source code along with the NetSim standard version also. And users can use their own components like the technology is required as per their need in standard and professional versions of NetSim. And professional version of NetSim, it's basically designed for the industries like where we will be having the mobile operators, etc. So many of the mobile operators have started using NetSim professional version, and they are undergoing their analysis in 5G module itself. So these are the three versions of NetSim. So in this session, I'll be using the NetSim standard version, using which we'll be going through the 5G module. And talking about the other technologies present in NetSim, we have the basic component, which is the Internet Works module, which contains the Ethernet, then WLAN, then other propagation models, etc. And then we have other technology libraries like the legacy network, which is pure Aloha and slotted Aloha. Then for modeling the firewall and etc., we have the advanced routing component. And for wireless communication, which contains multiple hops or routes, we have the MANET module in NetSim, which is the component 4. Then we have the software defined networks, where we can make one of the device as a controller, and that device can control other devices present in the network. Then we have the sensor networks, that is IoT and WSN. And the IoT module of NetSim also supports the RPL protocol, where we have the parent ID, neighbor, and sibling, using which the route is formed. And also then we have the cognitive radio network, which is purely based on the 802.22 IEEE standard, where we have the primary user and the secondary user and the spectrum sensing going on. And then coming to the component 8, it's a 4G network, which is the LTE. And then we have the vehicular ad hoc network, so which is used for vehicular communication, where we have the RSUs and other vehicles present. So vehicles can move throughout the environment, and the data transmission can take place from vehicle to vehicle or from vehicle to any infrastructure. And the vehicular ad hoc network module in NetSim has a direct interface with the open source tool, which is Sumo. And Sumo is basically used for the road simulation purpose. So it's easily interfaced with Sumo. And then coming to the technology which we are going to deal with now during the session, that is a 5G NR module, which is purely based on the 3GPP 38 series. So we have the full stack covering from SDAP, PDCP, RLC, etc., and with the propagation models and different frequency bands in 5G. Then coming to the component 11, we have the satellite communication network, where we have a geostationary satellite, and we have the KU band and the KA band, etc. And then for the industries and defense purpose, we have the military radio network, where we have the different frequencies like HF, VHF, and UHF, and the bands associated with those frequencies, etc. And for the live application transfer, we have the network emulator module. So this is basically the overall technologies which are present in NetSim. Now, coming to the modeling of network and then designing the network part, like I said, we have a graphical user interface, which is easy to in which we can easily create a scenario by just dragging and dropping the devices. And as you can see in the right side, NetSim will automatically take care of the scripting part of the scenario created. So as the user drags and drops the devices, the properties and other parameters associated with the device will be scripted in the background by NetSim. So this will be in an XML file which can be edited by the user also. And after the simulation, NetSim will provide a result dashboard window where we have the overall network performance present in the form of tables. So, and also we have the packet trace, event trace, and other log files, which can be used for deep analytical purpose. And for the documenting part, we have the plots option also, which gives an application throughput plot over time. And for the visualization purpose, we have a packet animator. So from one end device to other end device, how the packet flows will be given to the user in the form of an animation. And we have different color codes for different packets, like for control packets, we have the blue color. And for the data packets, we have the green color. And while transmitting, some packets may get errored or collided. For that, we have the red packet color packets. So overall, packet flow can be visualized using the packet animator window. Now, coming to the analysis part, we have a CSV file that is a packet trace window. So overall information about the packet will be logged into a CSV file called the packet trace. So we'll be going through all this in the software also. I'm just demonstrating it prior to the hands-on session using a PPT right now. And like I said, the standard version and professional version of NetSim comes with the protocol source codes also. So the source codes will also be shipped to the customer when they purchase NetSim. So we have the protocol source codes library where we have all the protocols listed out, and which can be easily edited using the Visual Studio, Community Edition or higher versions. So users can easily develop their own algorithms of protocols using the standard or professional versions of NetSim. And we can easily interface with the MATLAB tool using the socket interface program of NetSim. So easily the file layer performance and everything of different technologies can be analyzed by interfacing it with MATLAB. Already we have developed many projects using the NetSim MATLAB interface, like different attack projects in IoT, etc., like sinkhole attack, then leech project, etc., which have been developed by interfacing with MATLAB. And for analyzing the live traffic between real devices, we have the NetSim emulator module. So users can connect NetSim to a real hardware and interact with live performance using the NetSim emulator module. So this is also an add-on module which user can opt to if it's required. So before going to the 5G, we'll first go through the NetSim software. So this is basically the home screen window of NetSim. So some of you might be familiar with NetSim, and some of you might be using the older versions of NetSim, say V9, V10 or V11. So this is the latest version of NetSim, that is version 13.0. And we have made major changes in the home screen window itself when compared to the older versions of NetSim. So for creating a network, all the technology libraries are present and displayed here itself in the home screen window, like internetworks, legacy network, mobile ad hoc network, etc. So users can easily create a scenario by clicking on the preferred technology. And coming to the left side of the screen, we have a new simulation window where all these technologies are displayed.
Excuse me, sir.
Yes, sir. Yes, ma'am.
Sir, actually the slide which you are showing and what you are explaining, I think it's different, sir. It's showing the overview of NetSIM 5G.
Okay, so are you seeing a NetSIM home screen window or the PPT now?
PPT, sir.
Is it okay now, ma'am?
Yes, sir.
Okay, okay. Thank you. Yeah, sorry about that. I think I was sharing the PPT alone. So this is the home screen window of NetSIM. So this is the latest version, that is NetSIM standard v13.0. Like I said, many of you might be using NetSIM and will be familiar with the older versions of NetSIM. So there has been a drastic change in the home screen window of NetSIM itself when comparing with the older versions of NetSIM. Like we have the different technologies present here, like the internet network, the legacy network, mobile ad hoc network, etc. All listed out here, where user can select the required or preferred technology and create their own scenario. And yeah, coming to the left side, we have the new simulation window where user can create a new scenario. Then we have the your work option where all the all the saved experiments will be present. So right now this is empty since I haven't saved anything. So NetSIM will provide a workspace also. So you can see here the current workspace name, NetSIM 13.0 standard default. So NetSIM will provide a workspace feature where user can create their own workspace and save their experiments. So this will avoid the experiment clash between different users. Like if NetSIM is installed in a common system and multiple users are using NetSIM and saving their experiments or modifying the code, there might be chances of data loss. So to avoid that, we have the workspace option where user can easily create a new workspace and develop their own algorithms in that workspace alone, and also save the experiments in that workspace. And by saving this experiment in workspace, if they want to use the same experiment in future, it's easy to open here using the your work option. And also we have many inbuilt examples for all the technologies present in NetSIM, from internet works till the satellite communication. So all the pre-saved examples will help the user in understanding the technology more. And also there are individual manuals available for each technology, which can be easily accessed using the book icon present here. And for the deep analytical purpose, we have also some experiments present here, which can be used in the labs also, like the understanding network performance, then bottleneck server analysis, etc. So there are 30 plus experiments also present, which will also be available with the NetSIM tool. So yeah, now moving to the 5G module in NetSIM. Before that, I'll show you the grid environment where we can easily design a network. So I'll just click on Internet Works module. So this is the design window where user can create a network. So you can see the devices present in the network at the top ribbon. So for Internet Works library, we have the node, which is a wired node and a wireless node. Then the layer 2 and layer 3 switches, then router and the access point present. So it's easy to create a network. You just need to select one device and just click on the grid environment where the device will be automatically dropped. So now I'll drop a layer 2 switch, and to connect the devices, we have the wired or wireless link. So it's easy to connect the devices also. You just need to click on one device and then click on the next. So it will automatically connect the devices. And NetSim will automatically detect the wired and wireless connection. So when it comes to an access point and wireless node connection, there will be a wireless link present. So when you click on the wired or wireless link and connect these two, NetSim will automatically detect the wireless connection and connect it using a wireless link. So this is how a network can be designed in NetSim. And for configuring different parameters in NetSim devices, we have, if you right click, we have the properties where we have the TCP IP stack. So we have the application layer, transport network, and interface layer, where we have different layers like physical layer, data link layer, and network layer. So using which the properties of devices can be configured. So like in the transport layer, we have different TCP congestion control algorithms, etc. And for the modified property to have an impact on the simulation, you just need to click on OK button here. And for modeling the traffic, like I said, NetSim is a packet level simulator. So there will be packets transmitted from one device to the other. So the data transmission will also be in the form of packets. So to model the traffic between two end devices, we have the application option here, where you can enter the source ID and destination ID. That is basically the end devices. So here it's the wired node and the wired node 1 and 2. And we have different application types like CBR, custom, peer-to-peer, email, HTTP, etc. And also different methods like unicast application, multicast from one source to multiple destination, and broadcast from one source to every end devices present. And user can choose the transport protocol, either UDP or TCP here. And then we can, since this is a packet level simulator, you can determine the size of a packet. So by default, it will be a 1460 bytes packet. And inter-arrival time means the time interval at which a 1460 byte of packet is transmitted. So this will form up the rate of transmission. So if you click on OK, an application will be automatically created from one end device to the other, like that is from the source specified to the destination. And I'll simulate a scenario. So before moving to the 5G module, I just wanted to show you the NetSim user interface. So it will be easy when going to 5G module of NetSim. So I'll enable the packet trace. So these are the log files present. Now to run a simulation, it's easy. Just click on run, where we have the simulation time specified. So I'll give 10 seconds for now. So this is a virtual time and not a wall clock time. So the simulation will start from 0 second till the time specified here. And we have different options for packet animation. And once you click on OK, a console window will open up where the simulation progress can be observed. So after the simulation, there will be multiple windows opened by NetSim. So one will be the packet animation window, where we have the visual packet flow represented here. So these are the data packets transmitted from the source to the destination. So initially the source will transmit the data to the layer 2 switch present, and from the layer 2 switch it will be moved transmitted to the destination through the wired link. And also we have a result dashboard where we have the application throughput, the delay of application, etc. listed out per application. So if you have multiple application, the delay and throughput obtained for each application will be listed out here in the application metrics. And then in the left panel, we have different metrics like Q metrics, then UDP metrics if UDP protocol is chosen, and the access to the plots. And for the filing purpose, we have the export result option. So export result will export the overall result of the simulation into a CSV file, which can be backed up and used for further future uses. And if you want to print the result in the form of an HTML format, we have the print result option. Yeah, and coming to the packet trace. So since this is a large CSV file, it might take some time to load. So this is the NetSim packet trace file. So the overall information about each and every packet transmitted during the simulation will be present in this trace file. So this will be a large CSV file. So we have different types of packets, and all the packets will be listed out here with their source ID, the destination ID, that intermediate transmitter and receivers of the packet, then the packet ID. Say we have many packet IDs present here. So, and then sometimes some packets may be divided into segments. So for those we have the segment IDs. Then layer-wise arrival time, end time, etc. So for each and every packet, all the details will be listed out here in the packet trace window, and also the payloads in each layer. So we were setting a packet size of 1460 bytes. So in the application layer, the payload is 1460 bytes, and in the transport layer also it's 1460. And when it comes to a network layer, an 8 bytes overhead has been added. And then when it goes to the MAC layer, again some payload has been overhead has been added. And similarly, when it comes to the file layer also, overheads will be added, and this will be the overall packet payload present in the file layer. And with we have the packet status field where we can check whether a packet is errored or collided or successfully transmitted, etc. So for the deep analytical purpose of the simulation, we have the packet trace window. And also we have the plots window. So here we have the plots, and it's the link throughput plot and the application throughput plot. So this is an instantaneous and cumulative moving average plot. So the application throughput will be plotted against time from 0 second to till the end of the simulation. So the throughput at each time interval can also be checked using the plot window. And for accessing the source data, we have the source data option here, which gives the raw data of the plot generated. So these are the basic things about NetSim. So we also have some different manuals present. So we have the user manual where we have the detailed informations and sections from installing NetSim to all the advanced features present in NetSim, like how to set the generation rate, then how we can interface with the software, etc. All are listed out in the PDF and is available with NetSim. Now we'll be looking at the 5G module in NetSim. So first we'll go through the PPT where we'll get an understanding of the 5G, and then we'll go to the NetSim software, and we'll also look through certain examples which will help us gain some knowledge about 5G. So in NetSim, the 5G module is basically a full stack end-to-end packet level simulation of 5G network. So we'll be having some end devices like user equipment, a server, etc. And the data transmission can take place either from the server to the user equipment or from in the reverse direction. So we have some abstract model of radio frequency propagation and the physical layer performance. And yeah, many of the customers use a combination of both the system level simulator and also the link level simulator. So for the RF propagation part, they will be using the MATLAB and they will be passing the RF propagation part to the NetSim and analyzing the network performance in the 5G module of NetSim. So 5G basically has two deployment architecture. That is a standalone architecture and a non-standalone architecture or the dual connectivity. So NetSim has both the standalone and non-standalone architecture models. So in standalone architecture, it will be only the 5G part. So there will be no other things, like there will be just 5G communication happening and the 5G base station will be present. 5G core devices, etc. will be present. When it comes to the non-standalone architecture, you can interact between the 4G and 5G base stations. So you will be having a 4G base station and a 5G base station, and depending upon the settings, the data transmission will take place through the 4G and 5G base stations in dual connectivity mode or the non-standalone mode. So there are different deployment options present in the non-standalone architecture, which we'll be seeing through the session. And different applications are also present here, like voice, video, FTP, email, etc. And these applications will be over all the layers of network stack, that is the TCP/IP stack. So you can model either a voice application or a video application or FTP from one end device or a server to the user equipment. So this will be transmitted all the way through from a server side for a data network to the 5G core, and then to a base station, and then to the UE. Now, basically 5G core comprises of three devices. One is the AMF, then we have the UPF and the SMF. So there will be many AMF, SMF and UPF present, but NetSim currently supports only one AMF, SMF and UPF. So we'll be going through these devices. So and coming to the data link layer, we have the MAC scheduler also, which has proportional fair MAC scheduling, round robin match throughput, and strictly fair, based on which when there are multiple user equipments present, the data will be divided among them based on this MAC scheduler algorithms. And also we support different frequency bands, that is the sub-6 gigahertz, that is FR1 frequency bands, and 24 gigahertz to 54 gigahertz, that is the FR2 frequency bands for across all the carrier widths. So NetSim also has bandwidth supporting from 10 megahertz till 400 megahertz based on the frequency band selected. And also there are flexible subcarrier spacing from 15 kilohertz to 120 kilohertz, and this subcarrier spacing will be purely based on the numerology selected. So NetSim also supports numerology from 0 to 3, and the numerology 3 will be available for the FR2 frequency bands. And we have different link adaptations like the MCS to change the MCS based on the channel quality index, that is CQI. Then different modulation schemes are also supported here, like BPSK, QPSK, 16 QAM, 64 QAM, 256 QAM, etc. And also different bands. So basically the bands will be either a time duplex division or frequency duplex. So NetSim supports both TDD and FDD bands, and we also have different ratios for downlink and uplink applications also. So we'll see what is an uplink application, what is a downlink application, etc. using the NetSim software. And like in the real world, mobile won't be in a stationary position. It will be moving throughout. So suppose person A is standing in a place, and if he is traveling, the signal will be available in the mobile while he is traveling. So when he moves from one place to another, the control of the user equipment will be handed over to some other base station on the way. So to observe those also, we have the mobility and handover feature in NetSim. So using which we can model a mobility or model in a user equipment. So the user equipment will be moving throughout the grid environment as we determine. And then if there are multiple base stations available, the control of the user equipment will be passed to the next base station as it moves away from the first base station. And also we can model a scenario with hundreds of UEs and GNBs in NetSim. So like I said, the core devices are limited to one, but coming to the RAN part, we can have hundreds and hundreds of GNBs and UEs. So basically the 5G library is designed for mobile network operators and researchers and who are pursuing their PhDs and other researchers in the 5G domain. So we have using the 5G module of NetSim, we can analyze the throughput and latency of the network, then capacity of a network, I mean the 5G network. Then if we want to determine the power and bandwidth, we can use NetSim 5G module for that also. And we have different indoor cases and outdoor cases also present as per the 3GPP standards. And we also support the beamforming and MIMO, that is multiple input, multiple output. Then we have the handover and mobility, etc. And for research and purposes, universities and other research institutions are also conducting their researches using the NetSim 5G module. Now coming to the in-depth part, like I said, we have the RAN interface in 5G, which is basically a interface between the user equipment and the base station. So that's called a RAN interface. There we'll be having flexible subcarrier spacing based on the numerology selected. And we have operating bands, and the most commonly used operating band is the N78 or the C band, which is also called as 3.5 gigahertz mid band. And we have the other bands like N258, which is 26 gigahertz, and N261, which is the high band also. So all these bands are supported in NetSim. And as per the 3GPP standard, we have different CQI MCS tables also present. So the overall data transmission will be taking place, and at the end, the throughput will be obtained based on a number of calculations taking place in the background during the simulation. And also we have the uplink and downlink physical channel, that is PDSCH and PUSCH. And for 5-layer, different modulation schemes are present. And coming to the antennas or the MIMO part, we have different TH and RX antennas, that is the transmit and receive antennas present in GNB and UE. So in the GNB, there will be a single antenna to a multiple antennas. So we support from antenna count 1 to 128 in the GNB and from 1 to 16 in the UE. So if you are modeling a network with multiple antennas, GNB supports up to 128 antennas and UE supports up to 16 antennas in NetSim. And the MIMO spatial channel model is based it's based on the spatial multiplexing and not the transmit diversity in NetSim. And for the beamforming gain, we have the eigenvalues based on the H matrix present here in NetSim. And for the path loss calculation, it's strictly based on the 3GPP standard. So in the 3GPP standard, we have different path loss calculations present for different scenarios, like there is a rural macro scenario, urban macro scenario, urban micro scenario. And the path loss calculation and the range will be different for different cells present here. So based on that, we have the path loss calculation model in NetSim. And for the fading, we have the Rayleigh fading with eigen beamforming. So like I said, in the RAN interface, we have different cells available or the environments available based on which the path loss calculation will take place. That is the rural macro, urban macro, and urban micro. And if you want to model an indoor scenario, we have the facility to do that also. So the UE can be either indoor or outdoor in a scenario. And also you can determine whether the user equipment should be within line of sight or a non-line of sight from the base station using the LOA state. So these are the features present in the RAN part. So next comes the 5G core. So mainly the 5G core will be used for simulating end-to-end IP connectivity simulations. So like all the devices in the 5G core will be having IP address, and for from one end device with an IP address to another end device, user equipment. So the end-to-end IP connectivity will be done here using the 5G core device. So user can connect multiple UEs to an internet or cloud using the 5G core device. So we'll be having the user equipment and the base station at one end of the core, and then the data network or the cloud at the other end of the core. So data transmission can take place from cloud to the user equipment or the reverse. Suppose we are downloading some data from a cloud. So from the cloud, it will be moving to a transmitter to the core devices, and from core to the base station, and then to the user equipment. And if we are uploading something, it moves in the reverse direction. So for these purposes, we also have the core devices. And in the RAN part, we'll be having multiple GNBs. And all these GNBs will be connected to the 5G core devices, like the AMF, SMF, and UPF. So like I said, we have different deployment architectures. One is the standalone and the non-standalone. So in standalone, there will be only the independent 5G core devices, and no LTE core devices or base stations will be present here. And in the non-standalone architecture, we have both the LTE and 5G radio access technologies with 5G and LTE core devices present. And when it comes to the non-standalone architecture, we have different deployment options like option 3, 3A, and 3X, where we have the LTE core device. Option 4, 4A, option 7, 7A, and 7X, where we have the 5G core devices. So we'll be going through all this in the NetSim 5G module also. So first, we'll go through the 5G module in NetSim. So I'll just select the 5G module here. Since this is a large module, it may take some time to load. So yeah, so this is what I have been explaining, the standalone architecture and the non-standalone architecture. So initially there will be a setup window where we can select the required deployment architecture, and then we can also select the grid environment. So by default, it will be a 1 kilometer grid. So in x-axis and y-axis, we'll be having 1 kilometer range. And if user want to increase the range, they can just edit the field present here in the grid length. And in the standalone architecture, we'll be having the 5G core and 5G RAN. And when it comes to the non-standalone architecture, we have different deployment options, and based on which the 5G core or the LTE core will be present. So each deployment architecture for the option is having different master cell and secondary cell. So when it comes to option 3, 3A and 3H, the LTE base station will be the master cell. When it comes to 4 and 4A, the 5G base station will be the master cell. And when it comes to 7, 7A and 7H, again the LTE base station will be the master cell. So first we'll see the standalone architecture. So I'll just click on OK. So these are the core devices, 5G core devices present. So we have the AMF, the SMF, and the UPF. And all these devices are connected to a layer 2 switch. So mainly the AMF will handle the initial UE messages from the base station to the UE, etc., and to the core. And SMF will be serving as a control plane entity. So this SMF device will be responsible for the session management and also assigning IP address for the sending uplink data. Further, the SMF will also provide some message to the UPF, which is a PFCP message, which is a protocol function message to update the data. So the purpose of using a UPF is to connect the devices to the external data network. So this is a user plane function, which is UPF, and the cloud part or the data network part will be connected to the 5G core via the UPF. And all the data transmission will take place through the UPF link here. And when it comes to the control plane part or the control packet transmission, all the control packets will be transmitted via the AMF. So these are the devices present in 5G. So we have the data network part where we have wired or wireless node, layer 2 switches, etc., router, etc. And we have the 5G core, which will be automatically placed onto the grid environment. And in the base station, we have GNB and ENB. So since we have selected a standalone architecture, the ENB is faded out here. So then we have the user equipment, and for modeling the indoor scenarios, we have the building here. So we'll see the base station or the G node B first. So I'll just click on G node B icon here, and I'll drop it to the grid environment. So you can see here, as we drop a GNB, it will be automatically connected to all the 4 devices. So you can see 3 links connected to the GNB here. This indicates the base station to the 5G core connection. So there are different interfaces also present. So the GNB will be connected to all the core devices through a layer 2 switch. So for AMF, we have the layer 2 switch 5. For UPF connection, we have the layer 2 switch 4. And the layer 2 switch 6 is basically for the GNB to GNB connection. So I'll show here. So you can see here the GNB connection will take place through the layer 2 switch. So in 5G, for each interface, we have some specific names. So the connection between the AMF and the SMF, this interface is called the N11 interface. So if you go to the properties of AMF, we can see here two interfaces. One is the N11 interface, then we have the N1 and N2 interface. So N11 interface denotes the connection between the AMF, that is access and mobility management function, and the SMF, that is the session management function. So here for this interface, there will be a particular IP address assigned in the network layer. So this will be present in the interface 5G N11 network layer. And in the data link layer, we will be having the MAC address for this interface. And in the physical layer, we have the connection medium and the device to which it is connected to. And next is the connection from GNB to the AMF and the SMF. So this connection is called the N1 N2 interface. So from the GNB to the AMF and SMF, we have the connection which is called the N1 N2 interface. So GNB will be connected to the AMF via the layer 2 switch 5. So this connection is indicated here as the N1 N2 interface. So AMF is connected to the layer 2 switch via the N1 N2 interface, and this layer 2 switch is connected to GNB via the N1 N2 interface. And also there will be an IP address assigned for this interface. So here it's the 10.0.0.7. This is the IP address assigned for this particular interface of AMF. Similarly, SMF also has multiple interfaces. So SMF, like we saw now, we have the interface between AMF and SMF called the N11 interface, which is already present here with an IP address assigned. Then for the SMF to UPF connection, and for the data to get transmitted from SMF to UPF, we have a link here, and this interface is called the N4 interface. So you can see here an IP address will also be assigned for this interface. That's what the core is meant for, end-to-end IP connectivity of devices. And coming to the GNB, sorry, we have different interfaces present here. So one interface will be from the GNB to the AMF, that is the N1 N2 interface, and with an IP address assigned. Then the next interface of the GNB will be the connection between GNB and the user plane function or the UPF through layer 2 switch 4. So this interface is called the N3 interface. So this denotes a connection between user plane function or UPF and the GNB. And for the GNB to GNB connection, we have the HN interface with an IP address assigned to that interface also. So the HN interface is basically used for handover procedure in NetSim. So when a UE control is to be transmitted from